For months, astronomers watched it glide through the dark, a fragment of ice and rock, no larger than a small city, drifting on a trajectory older than memory. It appeared first as a smudge of light in the automated surveys, 1 pixel among billions, unremarkable except for its speed. The telescope in Chile that found it on July 1st, 2025, flagged the object immediately. Not because it was bright, not because it posed any danger, but because the mathematics of its motion revealed something unsettling. It wasn't ours. The comet moved through our solar system like a traveller passing through a train station, following a path shaped by forces from beyond the sun's reach. Its orbit bent into a hyperbola, that open curve of objects unbound by our star's gravity, the signature of something interstellar. The third such visitor ever confirmed, the largest, the fastest, a messenger from a stellar graveyard billions of years distant, carrying chemistry forged when the Milky Way was young and violent. At first it seemed harmless, a cosmic relic on a flyby route, destined to pass the sun and vanish back into the void between stars. Astronomers calculated its perihelion, its closest approach to our star, scheduled for late October. They tracked it through Mars's orbit in early October, watched it slip behind the sun's glare later that month, and prepared for its re-emergence in November. A rare opportunity to study material from another stellar system, yes, but nothing more than that, until someone refined the calculations. The new trajectory models arrived in fragments, built from weeks of accumulating data as the comet warmed and brightened. Professional observatories and amateur astronomers alike contributed measurements, each adding precision to the orbital solution, and with each new data point, the picture shifted. The comet wasn't just passing through our solar system at random. Its path aligned with something specific, something massive, something that shouldn't be part of any natural wanderer's itinerary. Jupiter. In March 2026, the interstellar comet will pass within 54 million kilometers of the gas giant and its court of moons. Not a collision, but an encounter precise enough to raise questions that most scientists prefer not to ask aloud. The probability of such alignment occurring by chance is vanishingly small. The mathematics work, but they work too well, like finding a letter addressed to you in a bottle washed up on a deserted shore. You watch the data streams from Hubble, Webb, and ground-based telescopes accumulate on your screen. Spectroscopic signatures revealing unusual chemistry. Nickel where there should be iron, carbon dioxide where water should dominate, an anti-tail, a jet of material pointing toward the sun rather than away from it, defying the normal rules of cometary behavior. Each anomaly explicable individually, each one natural perhaps, but together they compose a pattern that resists comfortable explanation. Scientists can't decide whether to celebrate or panic, because if this is guidance, if something about this ancient traveller's path toward Jupiter isn't coincidence, then we're watching the universe operate according to principles we haven't learned yet. And the window to understand is closing. The comet will reach Jupiter in 4 months, perform whatever interaction physics or something else has arranged, and then accelerate back into interstellar space, unreachable, forever beyond our instrument's grasp. The observatory networks are mobilizing. Juno orbiting Jupiter prepares to turn its sensors toward the approaching visitor. Europa Clipper, JUICE, Psyche, and a dozen other spacecraft scramble to adjust their observation schedules. Every major telescope on Earth and in orbit receives new target coordinates. The astronomical community recognizes what's at stake. One chance, one alignment, one mystery hurtling toward its conclusion at 130,000 miles per hour. And beneath Jupiter's radiation belts, beneath the crushing magnetosphere, the icy moons wait. Europa with its buried ocean, Ganymede with its magnetic field and ancient ice, Callisto with its scarred, preserved surface. Worlds that might already harbour chemistry on the edge of life, or might be waiting for a delivery from the stars. The comet carries something. Organic molecules, complex chemistry, material processed by billions of years of cosmic radiation and deep time. When it passes through Jupiter's system, some of that material will be left behind, dust grains captured by the giant planet's gravity, molecules scattered across the orbits of the moons, seeds perhaps, or catalysts, or simply debris. We don't know yet which it is, but we're about to find out. The Survey telescope in Chile's Atacama Desert operates like a mechanical sentinel, sweeping the sky in automated patterns every clear night. It's part of the ATLAS network, the Asteroid Terrestrial Impact Last Alert System, designed to catch objects that might threaten Earth. 4 robotic eyes scattered across the globe, each one photographing vast sections of sky, comparing new images against archived ones, flagging anything that moves or changes or suddenly appears where nothing existed before. On the night of July 1st, 2025, one of those telescopes captured something moving through the constellation Sagittarius. A faint smudge, magnitude 11 or 12, barely visible even to professional instruments. The software tagged it as a potential comet or asteroid and sent the coordinates to the Minor Planet Center, the astronomical clearinghouse where all such discoveries are verified and catalogued. Within hours, other observatories confirmed the sighting. The Zwicky Transient Facility in California found pre-discovery images from late June. Additional ATLAS stations in Hawaii and South Africa located the object in their archives going back to early June. Each observation refined the position, each measurement tightened the orbital calculation, and with each new data point, the picture grew stranger. The object wasn't following a typical solar system trajectory. Its speed exceeded anything bound to the sun's gravity. When astronomers traced the orbit backward through time and space, the path didn't close into an ellipse. It opened into a hyperbola, that mathematical shape reserved for things passing through, not objects in permanent residence. The velocity told the same story, over 130,000 miles per hour relative to the Sun, fast enough to escape our star's gravitational embrace entirely. This was the signature of an interstellar visitor. You drift beside it in imagination, watching the solar system unfold before your approach. You've been falling through the galaxy for so long that the journey itself has become your only reality. 4 billion years, perhaps 7, perhaps longer. The star system where you formed no longer exists. The planets that once shared your orbit have been consumed by their dying sun or scattered into the void. You alone survived, ejected by some gravitational catastrophe in an epoch before Earth existed. For eons you travelled through the spaces between stars, through regions where the nearest sun is a cold point of light years away, where the cosmic microwave background provides more warmth than any stellar furnace. The radiation of deep space altered your surface chemistry. Cosmic rays bombarding your ice and rock, building complex molecules in the frozen dark. You are older than our solar system, older than the sun, a fragment of the Milky Way's violent youth, and now you fall toward a yellow star unremarkable among billions. The discovery announcement classified the object as 3I Atlas. The 3I designation marked it as only the third confirmed interstellar object in history. The first, 1A Oumuamua, passed through our solar system in 2017, moving so fast that astronomers only spotted it on its way out, too late to study it properly. The second, Tuai Borisov, arrived in 2019, a more cooperative visitor that behaved like a standard comet and allowed detailed observations. But 3 Atlas was different. Larger than both predecessors, discovered earlier in its approach, and carrying chemistry that didn't match anything in our astronomical catalogues. The initial observations seemed straightforward enough. Hubble Space Telescope imaging on July 21st revealed a teardrop-shaped coma, the cloud of gas and dust surrounding the comet's nucleus. The solid core measured somewhere between 440 meters and 5.6 kilometers in diameter, larger than most solar system comets, massive enough to hold together across billions of years of travel through the radiation and cold of interstellar space. The coma showed the characteristic fuzzy appearance of sublimating ice, material vaporizing as the comet warmed in the sun's increasing heat. Spectroscopic observations from ground-based telescopes revealed the presence of diatomic carbon, the blue-green glow familiar from countless solar system comets. Water vapor appeared in the spectra, though curiously muted. Carbon dioxide dominated the outgassing, which wasn't unprecedented but wasn't common either. The dust production matched what astronomers expected for a comet of this size at this distance from the Sun. Everything seemed normal, at least on the surface, but as more data accumulated through July and August, peculiarities began emerging. The orbit solution kept shifting. Not dramatically, not in ways that suggested observational error, but in subtle refinements that revealed a pattern beneath the apparent randomness of the comet's path. The trajectory wasn't simply hyperbolic, it was precise. The orientation of the orbit, its angle relative to the plane where Earth and the other planets circle the Sun, measured at only 5 degrees of inclination. For an object arriving from interstellar space, from random regions of the galaxy where no preferred direction exists, such alignment with the solar system's fundamental plane represented a statistical oddity. Most interstellar objects should arrive from any direction with equal probability. The sky is a sphere, and visitors from beyond should reflect that geometric truth. Yet through our Atlas approached nearly along the ecliptic, the flat disk where planets formed and still orbit. As if it knew where to find the solar system's centre of mass, as if it were aimed. The trajectory analysis revealed something else, something that transformed curious coincidence into unsettling pattern. When astronomers projected the comet's path forward through time, calculating where it would go after rounding the Sun, the orbital solution kept returning to the same conclusion. The comet would pass within 54 million kilometers of Jupiter on March 6, 2026. Not merely passing through the general region where Jupiter orbits, but encountering the planet itself, threading through the narrow corridor where the gas giant's gravity and magnetosphere dominate. Orbital mechanics operates on strict mathematics. The probability of a random interstellar object arriving from the general direction of the galactic center, entering our solar system, aligned with the ecliptic plane, and then passing close to the largest planet in that system, calculates to fractions of a percent. Not impossible. Nature permits coincidence. But astronomers have learned to distrust patterns that seem too convenient. Someone at the Jet Propulsion Laboratory ran the numbers 3 times, checking for errors in the calculation. The same result emerged each time. The comet's perihelion, its closest approach to the Sun at 1.4 astronomical units, positioned it perfectly for a subsequent encounter with Jupiter. The timing worked precisely. The angle of approach aligned with Jupiter's position in March 2026, Every variable in the equation cooperated to produce this specific outcome. It was like watching a pool ball sink into a corner pocket after bouncing off 3 cushions. Possible, yes, but requiring either extraordinary luck or deliberate aim. The observation teams began working extended shifts. Ground-based telescopes from Chile to Hawaii to South Africa tracked the comet nightly, weather permitting. Hubble allocated more observation time. Webb, the infrared eye studying the early universe from its station beyond the moon, turned its golden mirrors toward this ancient visitor and began collecting spectroscopic data that would reveal the comet's chemical composition in exquisite detail. Even the Transiting Exoplanet Survey satellite, designed to hunt for planets around other stars, caught glimpses of 3 Atlas as it crossed through the spacecraft's field of view. By September, the comet had brightened to magnitude 11, just within reach of large amateur telescopes. Astrophotographers around the world began capturing images showing the comet's growing coma and the faint tail stretching away from the sun. The images accumulated in online databases, each one adding incremental data to the growing portrait of this interstellar wanderer. And with each new observation, the Jupiter encounter looked less like coincidence and more like destination. You watch the data compile in the observation logs. Position measurements accurate to arc seconds, velocity vectors refined to meters per second, spectroscopic signatures passed into molecular abundances. The comet follows its calculated path with mechanical precision, neither accelerating unexpectedly nor deviating from the predicted trajectory. It behaves exactly as orbital mechanics predicts an object should behave, except that the prediction itself contains the mystery. Because the orbit that fits all the observations, the path that matches every measurement, is the same orbit that leads directly to Jupiter. Not approximately, not in the general vicinity, but threading the needle through the giant planet's sphere of influence with the precision of a guided missile arriving at predetermined coordinates. The question everyone began asking, though few voiced it in official publications, was simple and disturbing. What happens when an interstellar comet older than Earth, carrying chemistry forged in another stellar system, encounters the largest planetary system in our cosmic neighbourhood? The answer, if there is one, waits 4 months ahead. At the end of a trajectory that shouldn't exist, following a path that might be destiny or might be design, and we have no way to know which until the moment arrives. The mathematics of celestial mechanics reduces the universe to numbers: position and velocity, mass and distance, gravitational constants and angular momentum. Feed these values into equations refined over centuries, and you can predict where any object will be at any moment in time. The Moon's position 10,000 years hence, the precise instant when a distant asteroid will cross Earth's orbit, the trajectory of a comet falling through our solar system from interstellar space. The equations never lie. They cannot, they simply describe what is. When orbital dynamicists at NASA's Jet Propulsion Laboratory first calculated 3I Atlas's trajectory using early July observations, they arrived at a preliminary orbit that marked the object as definitely interstellar, but provided limited detail about its future path. The data was sparse, the measurements still accumulating. By late July, with Hubble observations and dozens of ground-based tracking stations contributing positions, the orbital solution refined dramatically. The eccentricity, the measure of how stretched or circular an orbit appears, came back at 1 to 3, definitively hyperbolic, confirming the comet would make one pass through our solar system and never return. The inclination measured at 175 degrees, which in orbital mechanics means the comet travels retrograde, moving opposite to the planet's direction around the Sun. but tilted only 5 degrees from the ecliptic plane. This detail alone merited attention. The ecliptic represents the disk where the solar system's mass concentrates, the plane where planets formed from the primordial cloud that birthed our sun. For an interstellar object to arrive aligned with this plane suggested either remarkable coincidence or something else. The perihelion distance calculated at 1.36 astronomical units, placing the comet's closest solar approach just inside Mars's orbit. The perihelion date, October 29, 2025. From these parameters, computers projected the comet's path forward through space and time, tracing where it would go after swinging around the Sun. The projection showed Mars first. On October 3rd, the comet would pass 0.19 astronomical units from the red planet, close enough that rovers on the Martian surface might detect particles from its tail. Then Venus on November 3rd at 0.65 astronomical units. Earth on December 19th at a comfortable 1.80 astronomical units, far enough to pose no threat but close enough for detailed observation from ground-based telescopes. And then Jupiter, March 16th, 2026, at 0.36 astronomical units, 54 million kilometers, 1/3 the distance between Earth and the Sun, close enough that Jupiter's powerful magnetosphere would wrap around the comet, close enough that the giant planet's gravity would noticeably perturb the trajectory, close enough that instruments aboard the Juno spacecraft orbiting Jupiter would collect data on the interstellar visitor from ranges typically reserved for studying Jupiter's own moons. The orbital analysts ran sensitivity analyses, testing how uncertainties in the measurements might affect the predicted encounter distance. They varied the comet's position within observational error bars, adjusted the velocity vectors by fractions of a meter per second, propagated these changes forward through the gravitational influences of all the planets and the Sun itself. The closest approach distance to Jupiter varied by a few million kilometers in these simulations, but the encounter itself remained fixed. No reasonable variation of the input parameters eliminated the Jupiter flyby. Someone calculated the probability. Start with the assumption that interstellar objects arrive from random directions in three-dimensional space. The sphere of possible approach vectors contains infinite points, but only a thin disk. The ecliptic plane and its immediate vicinity contains the solar system's planetary orbits. An object arriving randomly has perhaps a 5% chance of entering within 10 degrees of the ecliptic. 3 Atlas arrived within 5 degrees. Already unusual, but not impossible. Next, consider that Jupiter occupies a specific position in its 12-year orbit around the Sun. The comet must arrive not only in the ecliptic plane, but also at the correct time to encounter Jupiter in its orbital path. Jupiter's orbit measures roughly 5.2 astronomical units in radius. The volume of space the planet sweeps through in one orbit is vast, but the volume the planet actually occupies at any given moment is comparatively tiny. For a randomly arriving interstellar object to pass within 0.36 astronomical units of Jupiter requires timing as well as spatial alignment. The combined probability, accounting for both factors, calculated to approximately 0.4%, not impossible. 4 encounters in every 1,000 random arrivals might produce such geometry. But 3 Atlas represented only the 3rd confirmed interstellar object ever detected. The sample size was too small to invoke statistical averaging. Each object stood alone, and this one had threaded an improbable needle. The number haunted the analysts. Improbable doesn't mean impossible, they reminded each other. Improbable events occur constantly in a universe vast enough to generate countless opportunities. Somewhere among the billions of stars in our galaxy, unlikely alignments must be unfolding at every moment. We simply happened to witness one, but the precision bothered them more than the probability. Orbital mechanics treats every object as a point mass following paths determined by gravity alone. The equations assume nothing guides these objects beyond Newton's laws and Einstein's refinements. Yet when you examine 3i Atlas's trajectory in detail, plotting its path through the solar system like a road map, the route appears almost optimized. The comet enters the inner solar system along a path that minimizes unnecessary deviation, passes the Sun at a distance that avoids destructive tidal forces while allowing substantial warming and outgassing, then proceeds directly to the largest gravitational well in the planetary neighborhood. It's the trajectory you would design if you were planning an efficient tour of the solar system. Arrive, sample the inner system, visit the most massive planet, depart. All accomplished in a single hyperbolic pass requiring no orbital insertions, no powered maneuvers, no course corrections, just pure ballistic flight shaped by gravity. The numbers themselves tell a story. The perihelion velocity, the speed at which 3i Atlas passes its closest point to the Sun, measures approximately 52 kilometers per second. This velocity, combined with the Sun's gravity, determines the hyperbolic excess velocity, the speed the comet will carry when it escapes back to interstellar space. That escape velocity calculates to roughly 34 kilometers per second, slower than the comet's arrival speed because the Sun's gravity has extracted energy from the trajectory. But here's what makes the geometry remarkable. That specific velocity, combined with a specific perihelion distance and the specific orbital inclination, produces a trajectory that naturally encounters Jupiter on the outbound leg. Change any one parameter by even modest amounts, and the Jupiter encounter disappears. Make perihelion 10 million kilometers closer or farther from the Sun, and the comet misses Jupiter by tens of millions of kilometers. Adjust the arrival velocity by a few kilometers per second, and the timing shifts such that Jupiter occupies the wrong position in its orbit when the comet passes through. Alter the inclination by even a few degrees, and the paths no longer intersect. The trajectory exists in a narrow solution space where all the variables cooperate. It's not that the mathematics forces this outcome, it's that this particular combination of initial conditions, arrival speed, arrival direction, arrival timing, happens to produce a path that threads through the solar system's most interesting target. Celestial mechanics contains no concept of aim. Objects follow trajectories determined entirely by their position, velocity, and the gravitational field they inhabit. The comet cannot choose its path any more than a river can choose to flow uphill. Whatever velocity 3i Atlas possessed when it entered our Sun's sphere of influence, whatever direction it moved, those parameters were set billions of years ago, inherited from the ancient catastrophe that ejected it from its birth system, modified by countless encounters with the galaxy's distributed mass over eons of travel. Yet the result appears purposeful. You stand in the orbital dynamics laboratory, surrounded by monitors displaying trajectory plots and parameter tables. Coloured lines trace the comet's path through the solar system, weaving between planetary orbits like a needle through fabric. The Jupiter encounter point glows on the screen, marked with crosshairs and distance measurements. Everything checks, the calculations balance, the physics works perfectly, but the perfect is what troubles you. Because in nature, perfect alignment usually requires either vast numbers of attempts or deliberate arrangement. Roll a die often enough, and you'll eventually roll 6 sixes in sequence. But if someone hands you a die and you immediately roll 6 sixes, you start wondering about the die. The universe has handed us 3 interstellar objects. The first one, Oumuamua, arrived tumbling through the inner solar system on a trajectory that missed all major planets, departed quickly, and generated years of speculation about its odd shape and behaviour. The second, Borisov, behaved like a normal comet on a relatively boring trajectory that came nowhere near significant targets. And now the third arrives on a path precisely aligned to encounter Jupiter, the gravitational anchor of the outer solar system, the planet orbited by potentially habitable moons, the location where any visitor might learn the most about our cosmic neighbourhood. 3 objects, 3 trajectories, 1 perfect alignment. The orbital analysts update their calculations nightly as new observations arrive. The Jupiter encounter distance has refined from initial estimates of approximately 50 million kilometres to 54 million kilometres, with an uncertainty of less than 2 million kilometres. The encounter time has sharpened to March 16, 2026, with precision measured in hours rather than days. Every refinement confirms rather than contradicts the alignment. Someone jokes that maybe the comet is just naturally attracted to large planets. Someone else suggests we're experiencing observation bias. We only notice the interstellar objects that pass near interesting targets, while dozens of others slip through the system unobserved. These explanations satisfy the need to rationalize the improbable, to fit the unexpected into familiar frameworks. But late at night, when the telescopes track the comet across star fields, when the data streams compile into updated orbital solutions, when the numbers confirm themselves again and again, the same question surfaces in different forms. What if the alignment isn't accident? What if the probability isn't chance? What if the mathematics describes not randomness but trajectory? The equations cannot answer this. They can only describe what is, not why it is. And what is right now is a comet older than Earth following a path that intersects Jupiter with mechanical precision, carrying chemistry from another star system toward moons that might already be preparing to receive it. 4 months until we learn what the mathematics really means. Every comet is a clock wound backward toward the solar system's birth. As they approach the Sun, heat penetrates their frozen surfaces, liberating molecules trapped since the primordial disk condensed into planets. Water sublimates first, escaping as vapour that catches sunlight and forms the characteristic glow. Then carbon compounds, organic molecules, trace minerals. The process is chaotic, driven by thermal gradients and structural weaknesses in the ice. Jets erupt from random locations on the nucleus, pointing in unpredictable directions, creating the fuzzy coma and sweeping tails that mark comets as messengers from the cold outer reaches. This is how comets behave. This is what billions of years of observation have taught us. 3i Atlas was not behaving like this. The first anomaly appeared in images from the Gemini South Telescope in Chile on August 27, 2025. The comet displayed the expected coma, a bright condensed core surrounded by diffuse gas and dust. But emerging from that core, pointing not away from the sun but toward it, a narrow jet extended like an accusatory finger, an anti-tail. Spectroscopic analysis revealed it was composed of larger dust particles, material that should have been swept backward by solar radiation pressure, but instead pointed sunward, defying the fundamental geometry that shapes cometary appearance. Anti-tails are not unknown. They occur when Earth's viewing angle passes through a comet's orbital plane, creating a perspective illusion where the dust tail appears to point toward the sun even though it actually extends away in 3 dimensions. Astronomers checked the geometry. The angles did not support an optical illusion. The jet was real. Material actively ejected toward the sun rather than away from it, sustained over days of observation. Comets outgas chaotically because their nuclei rotate, because their surfaces are irregular, because pockets of volatile material sublime at different rates depending on local temperature and composition. The jets should wander across the nucleus as it spins, creating complex shifting patterns in the coma. But 3I Atlas's anti-tail remained stable, pointing toward the sun with mechanical consistency, even as the nucleus presumably rotated beneath it. This suggested either an unusual surface feature, perhaps a single large vent aligned with the sun-facing pole, or something else. Something involving sustained directional outgassing that should not be possible without active control. The spectroscopic observations from James Webb Space Telescope brought deeper mysteries. Webb's near-infrared spectrograph dissected the comet's light into its component wavelengths, revealing which molecules populated the coma and in what abundances. The dominant signal came from carbon dioxide, not water vapor. Most solar system comets are approximately 80% water ice by composition. They outgas primarily H2O as they warm, creating the characteristic hydroxyl emission that gives comets their blue-green glow. 3I Atlas was only 4% water by mass. The coma contained carbon dioxide at concentrations 20 times higher than water, a reversal of normal cometary chemistry. This alone might be explained by formation in an unusually carbon-rich stellar system, or by extreme radiation processing during billions of years in interstellar space. But the Webb data revealed other oddities layered beneath the obvious ones. Nickel. The spectra showed clear nickel emission lines, which was not unprecedented. Some solar system comets contain trace metals, but the abundance ratio troubled the spectroscopists. In typical comets, nickel appears alongside iron in roughly equal proportions, the 2 metals reflecting their cosmic abundance ratio forged in supernova. In 3I Atlas, nickel dominated overwhelmingly. The nickel-to-iron ratio exceeded normal values by orders of magnitude, approaching levels seen in industrial nickel alloys rather than natural cosmic dust. One researcher calculated that the nickel abundance relative to cyanide, a common cometary molecule, was higher than in any previously observed comet, including 2I Borisov, the previous interstellar visitor. This was chemistry that made no sense in natural formation scenarios. Nickel concentrates in planetary cores during differentiation, not in icy bodies formed in the cold outer regions of stellar systems. Finding it so enriched in a comet suggested either exotic formation conditions or post-formation processing of a type we have no mechanisms to explain. The outgassing rate provided another puzzle. Hubble observations from July estimated the comet was ejecting approximately 6 kilograms of small dust particles per second and 60 kilograms of large dust particles per second. These rates seemed reasonable for a comet of 3I Atlas's size at its distance from the Sun. But as the comet continued inward, approaching perihelion through September and October, the outgassing rate did not increase as steeply as thermal models predicted. Comets should brighten and become more active as they approach the Sun, responding to increasing solar heating. The relationship between distance and activity follows predictable curves derived from physics. 3I Atlas brightened. Yes, but more slowly than expected, as if some mechanism limited how much material could sublime even as temperatures rose. The comet reached magnitude 11 in September and hovered there, varying by less than half a magnitude over weeks when it should have been steadily brightening toward perihelion. This suggested a surface layer of some kind, perhaps radiation-processed crust, built up over billions of years of exposure to cosmic rays and interstellar ultraviolet light. Such crusts form on long-period comets and can insulate the interior, throttling out gassing. But 3I Atlas was not a long-period comet returning from the Oort cloud. It was an interstellar object that had never orbited our Sun before, never been warmed by our star. Its surface should be pristine ice, not insulated crust, unless it had been warmed by something else. The jet structure revealed additional strangeness when analysed in detail. High-resolution imaging showed the anti-tail was not a single stream but multiple filaments, narrow threads of material ejected with surprising collimation. Natural jets spread as they leave the nucleus, diverging into broad fans. These remained tightly focused, almost beam-like, extending tens of thousands of kilometers from the nucleus without significant dispersal. The physics of gas expansion argues against such collimation. When material sublimates from a comet's surface, it accelerates outward in all directions from the vent, forming a cone. The only way to maintain a narrow beam is through some form of focusing, either magnetic fields channeling ionized particles or geometric constraints that seem implausible in a natural ice body. Ground-based observers tracking the comet through September noted the coma's shape changed in ways that did not correlate with the expected rotation period. If the nucleus rotates and jets are fixed to surface features, you should see periodic brightening and dimming as active regions turn toward and away from Earth. 3. Atlas showed brightness variations, but they did not repeat on a clear period. The comet either rotated chaotically, possible but unusual for an object that had billions of years to settle into stable rotation, or the jets were not fixed to the surface. The dust grains themselves presented anomalies. Analysis of how the grains scattered sunlight revealed a size distribution that skewed towards smaller particles than typical comets produce. Small grains, roughly 1 micrometer in radius, were being ejected at velocities of 22 meters per second. Larger grains, around 100 micrometers, moved at only 2 meters per second. This velocity differential made sense from a physics perspective. Smaller particles are easier to accelerate, but the overall production rate of small grains exceeded what models predicted for natural sublimation processes. It was as if the comet was deliberately producing fine dust, grinding down material into microscopic particles more efficiently than thermal stress alone should accomplish. Researchers began proposing natural explanations. Perhaps the comet's unusual chemistry resulted from formation around a carbon-rich star, a red giant in its death throes enriching its planetary system with exotic elements. Perhaps the nickel enrichment came from the comet originating in a differentiated parent body that later shattered, with 3 Atlas representing a fragment that sampled core material. Perhaps the anti-tail was nothing more than a lucky alignment of viewing geometry combined with an unusually dusty outburst. Each explanation addressed one anomaly, none addressed all of them simultaneously. You watch the comet through November as it emerges from behind the sun, reappearing in the morning sky for observers in the northern hemisphere. Amateur astronomers with large telescopes capture images showing a comet that looks normal, fuzzy and diffuse with a faint tail. But beneath that familiar appearance, the spectroscopic data continues accumulating, each observation adding detail to a chemical portrait that refuses to make sense. The carbon dioxide dominance, the water deficit, the nickel enrichment, the stable anti-tail, the controlled outgassing rate, the collimated jets, the unusual dust production, the brightness behaviour. Any single oddity could be explained. Together they sketch something that sits uncomfortably at the boundary between natural and impossible. Not definitively artificial, nothing in the data screams manufactured, but not quite fitting the template of how comets should behave when billions of years of ice finally meet stellar heat. Scientists debate these anomalies in conference calls and preprint servers, proposing mechanisms and countermechanisms, citing precedents from solar system comets that showed similar but less extreme behaviours. The scientific method demands parsimony, the simplest explanation that fits the facts. And the simplest explanation remains that 3I Atlas is a natural comet with unusual but not impossible properties. But simplicity and truth are not always synonyms. And as December approaches, as the comet continues outbound toward its March rendezvous with Jupiter, the feeling grows that we are watching something perform rather than simply behave. Something following a script written in chemistry and physics but executed with precision that natural chaos rarely achieves. The comet will not answer these questions. It simply continues, outgassing molecules that do not belong together in these proportions, maintaining jets that should not remain so stable, carrying chemistry that should not exist in a body formed in the cold outskirts of a dead stellar system, all of it aimed at Jupiter, all of it arriving exactly on schedule. Jupiter hangs in space like a miniature solar system unto itself. The planet contains more mass than all other planets combined, a gas giant whose gravity shapes the architecture of everything around it. Its magnetosphere extends millions of kilometers into space, a bubble of charged particles and magnetic field lines that would engulf the Sun if the two switched places. Within this domain, 67 confirmed moons orbit in families and resonances, from tiny captured asteroids to worlds larger than Mercury. 4 of those moons matter more than the others. Europa orbits closest among the major satellites, locked in gravitational dance with Jupiter's tremendous mass. Tidal forces flex the moon's interior, generating heat through friction as Europa stretches and compresses during each orbit. That heat prevents the subsurface ocean from freezing despite temperatures at the surface reaching -160 degrees Celsius. The ice shell averages perhaps 15 kilometers thick, thin enough that fractures and ridges crisscross the surface, thin enough that water occasionally erupts through cracks to create temporary geysers. Beneath that ice lies an ocean estimated at 100 kilometers deep, containing twice as much water as all of Earth's oceans combined. The Galileo spacecraft detected induced magnetic fields during flybys in the 1990s, evidence that salty, electrically conductive water moves beneath the frozen crust. Spectroscopic observations revealed surface compounds including hydrated salts, sulfates, and tentative detections of hydrogen peroxide. The chemistry suggests active exchange between the ocean and the ice above it, between the water and the rocky seafloor below it. That seafloor matters immensely. Unlike the ice sandwich structure of Ganymede and Callisto, where oceans float between layers of ice with no contact to rock, Europa's ocean touches silicate minerals. Water interacts with stone. Chemistry becomes possible that cannot occur in isolated ice layers. Hydrogen bubbles up from reactions between water and iron-rich rocks. Sulfur compounds leach from hydrothermal systems. The conditions mirror, however imperfectly, the deep ocean vents on Earth where chemosynthetic life thrives without sunlight, harvesting energy from chemical gradients rather than photosynthesis. If life exists anywhere in the solar system beyond Earth, Europa represents the most likely refuge. Ganymede orbits farther out, the largest moon in the solar system, exceeding even Mercury in diameter, though not in density. It possesses its own magnetic field, the only moon known to generate one, suggesting a metallic core and internal dynamo. The surface displays two distinct terrains: dark, ancient cratered regions billions of years old, and brighter grooved regions showing evidence of tectonic activity, places where the ice crust fractured and reformed. Beneath that complex surface, magnetic field measurements suggest an ocean exists at depths around 150 kilometers, buried under thicker ice than Europa's ocean. The burial complicates access, makes exchange with the surface more difficult, reduces the likelihood of active chemistry. Yet Ganymede's size means it retains internal heat, and its ocean may persist for billions of years. The thickness of the overlying ice protects the ocean from Jupiter's radiation, creating a stable environment isolated from the chaos above. The ocean's depth remains uncertain, but estimates suggest it could exceed 100 kilometers, another world ocean larger than Earth's hydrosphere, hidden beneath ice shells, and possibly additional ice layers of different crystalline structure. Whether that ocean contacts rock or floats atop deeper ice layers determines much about its habitability. Rock contact allows chemistry. Ice contact means sterility. Callisto occupies the outermost orbit among the major moons, far enough from Jupiter that tidal heating barely affects its interior. The surface tells the story of 4.5 billion years without geological activity, the most heavily cratered landscape in the solar system, every impact preserved in the ancient ice. No tectonic features, no volcanic plains, just craters upon craters, layers of cosmic violence frozen in time, yet even Callisto may hide an ocean. Magnetic field measurements during Galileo flybys suggested electrically conductive layers at depth, likely a salty ocean heated not by tides, but by residual heat from the moon's formation and decay of radioactive elements in whatever rocky core exists. That ocean would be cold, isolated, ancient. Ammonia mixed with the water would lower the freezing point, allowing liquid to persist in conditions that should produce only ice. Callisto's ocean represents the most challenging habitability scenario. No tidal heating to drive circulation, no clear path for nutrients to reach the water from the surface or the deep interior. Just cold, dark water sitting beneath kilometers of ice, heated only by the faint glow of radioactive decay. If life exists there, it would be life in a tomb. Metabolism slowed to geological timescales, chemistry operating at the minimum threshold where molecules still interact. These three worlds, Europa, Ganymede, Callisto, form a laboratory for understanding how life might emerge in environments completely unlike Earth. They operate on different energy budgets, different chemical inputs, different timescales. Europa receives tidal heating and likely possesses hydrothermal vents. Ganymede retains internal heat and magnetic shielding. Callisto subsists on the bare minimum energy necessary to keep water liquid. Yet all three share fundamental requirements: liquid water, organic chemistry, energy gradients, time. And on March 16, 2026, an interstellar comet will pass through their neighborhood, carrying material from another stellar system entirely. You imagine the encounter from Jupiter's perspective, watching this ancient traveler approach through the magnetosphere's outer boundaries. The comet's coma, that cloud of gas and dust extending thousands of kilometers from the nucleus, enters first, neutral molecules and charged particles mixing with Jupiter's radiation belts. This solar wind pushes the comet's ion tail backward, away from the sun, but Jupiter's magnetic field begins interacting with the ionized material, bending and channeling it along field lines. Some of that material will be captured. Dust grains too small to resist Jupiter's gravity will spiral inward, some impacting the planet's atmosphere, others settling into orbits where they slowly spiral down toward the gas giant's clouds. Larger particles will scatter, some captured into temporary orbits around Jupiter, others deflected into new trajectories that might intersect the orbits of the moons. The organic molecules in the comet's coma, carbon dioxide, carbon monoxide, cyanide, nickel compounds, whatever exotic chemistry billions of years of interstellar radiation has synthesized, will spread through the system. Most will disperse, lost to space or consumed by Jupiter's atmosphere. But some fraction, perhaps a few kilograms, perhaps a few tons, will encounter the moons. Europa's thin oxygen atmosphere cannot protect its surface from this fallout. Particles will rain down on the ice, settling into cracks and fractures, possibly reaching places where the ocean connects to the surface through active geology. The radiation environment will immediately begin processing these new molecules, breaking them apart and recombining them with the existing surface chemistry. Ganymede's magnetic field provides some shielding, but material can still reach the surface, particularly in the polar regions where field lines channel particles down. The ancient cratered terrains will accumulate dust, and the younger grooved regions, places where ice tectonics might still slowly operate, could transport some of that material downward toward the buried ocean, a process measured in millions of years but inevitable given enough time. Callisto, furthest out and least geologically active, will simply accumulate whatever falls onto its surface. The material will sit there, frozen, waiting. No active processes exist to transport it anywhere. The ancient ice will preserve it indefinitely, another layer in Callisto's sedimentary record, a marker that once, billions of years after the moon's formation, an interstellar visitor passed nearby and left a gift. The question nobody can answer yet is whether this represents contamination, contribution, or communication. Contamination, if the material disrupts existing chemistry, introduces molecules that interfere with whatever processes might already be unfolding in those hidden oceans. Contribution if the molecules add to the chemical complexity, providing new building blocks for reactions that lead nowhere on their own, but might combine with native chemistry to create something unexpected. Communication if, and this remains the possibility nobody wants to voice in official publications, the delivery was not accidental. Astrobiology faces an ethical framework unprepared for this scenario. The Outer Space Treaty of 1967 addresses territorial claims and military use of celestial bodies. Planetary protection protocols govern how we design spacecraft to avoid contaminating other worlds with Earth life. But nothing addresses what happens when the universe delivers potentially biologically active material to places where biology might already exist or might be on the verge of emerging. Do we welcome it? Do we fear it? Do we attempt to prevent it? As if we could, the comet will arrive regardless of our preferences. The encounter was set in motion billions of years ago, when gravitational forces in a dead stellar system ejected this object into interstellar space. Whether its current trajectory represents pure chance or subtle guidance changes nothing about the fundamental outcome. In 4 months, the Jovian system will receive a delivery from beyond, and the moons will be forever altered, however slightly, by the addition of molecules forged in another star's light. Europa will receive it in an ocean already rich with chemistry, where the addition of even trace amounts of new compounds might catalyze reactions that would not otherwise occur. Ganymede will store it in ice, where billions of years from now, should the thick ice shell ever thin enough to allow exchange with the ocean below, those preserved molecules might descend to the deep water and begin their chemistry then, in an epoch when Jupiter's light has changed, when the solar system has aged. Callisto will keep it on the surface, a time capsule within a time capsule, demonstrable proof that interstellar material reaches the Jovian moons, and that the chemistry of one stellar system can mix with another across gulfs of space and time that should make such exchange impossible. The delivery will not be dramatic. No impact crater, no explosion. Just dust settling from space, molecules diffusing through thin atmospheres, particles accumulating at fractions of a nanogram per square meter. The change will be immeasurable by direct observation, detectable only through careful analysis of surface composition years or decades later, when missions land and collect samples. But immeasurable does not mean insignificant, because if life is a chemical process that begins when the right molecules meet under the right conditions with the right energy sources, then every molecule added to the inventory matters. And if those molecules come from an interstellar source carrying chemistry processed by billions of years of cosmic radiation, by conditions that exist only in the space between stars, then they represent chemical possibilities that the Jovian system cannot generate on its own. Seeds perhaps, or catalysts, or simply dust. We will not know which until we look, and we are running out of time to prepare. Time moves differently for astronomers than for the objects they study. A comet travels for billions of years through interstellar space, then crosses our solar system in months. Stars evolve over eons, but the window to observe a supernova's first light lasts only hours. The universe operates on scales both geological and instantaneous, and we exist somewhere between, always racing against deadlines we cannot control. For 3i Atlas, the deadline is absolute. Discovery came on July 1st, 2025, when the comet was still 4.5 astronomical units from the Sun, beyond Jupiter's orbit inbound. That distance provided breathing room, time to organise observation campaigns, time to analyse preliminary data, time to understand what we were seeing before critical moments arrived. But astronomical distances collapse quickly when objects move at 130,000 miles per hour. Every day consumed 3.5 million kilometres of the comet's journey. Every week brought it 24 million kilometres closer to perihelion. By late July, the comet had closed to 4 astronomical units. Hubble captured detailed images showing the teardrop-shaped coma and provided the first estimates of the nucleus size. Webb's infrared spectrograph began collecting data that would reveal the unusual chemistry. Ground-based telescopes from Chile to Hawaii tracked the comet nightly, building the orbital solution that eventually revealed the Jupiter trajectory. August saw the comet brighten from magnitude 12 to magnitude 11, crossing the threshold where large amateur telescopes could detect it. The Gemini South telescope documented the anti-tail. Professional spectroscopists measured the carbon dioxide dominance and the nickel anomaly. The comet crossed into the asteroid belt, still accelerating as the Sun's gravity pulled it inward. September brought 3i Atlas to within 2 astronomical units of the Sun. The brightness plateaued at magnitude 11 rather than continuing to brighten as thermal models predicted. The outgassing rate remained stable when it should have been increasing exponentially. The collimated jets maintained their structure, and the refined orbital calculations confirmed what everyone had begun to suspect. The Jupiter encounter was not a glancing pass but a precision flyby that would thread the comet through the giant planet's magnetosphere at a distance closer than most of Jupiter's inner moon's orbit. October arrived with perihelion looming. On October 3rd, the comet passed Mars at a distance of 28 million kilometres, close enough that the Perseverance and Curiosity rovers attempted to image it from the Martian surface, though the comet remained too faint for their cameras to detect clearly. Mars Reconnaissance Orbiter had better success, capturing spectra that added to the growing database of the comet's composition. Then came October 29th. Perihelion. The comet reached its closest approach to the Sun at 136 astronomical units, just inside Mars's orbit, and disappeared into the solar glare. For 2 weeks, observation became impossible from Earth. The comet sat on the far side of the Sun, invisible to ground-based telescopes, challenging even for space-based observatories. The SOHO spacecraft's coronagraph caught glimpses as the comet transited through its field of view, a faint smudge moving through the instrument designed to study the Sun's corona. But detailed spectroscopy, high-resolution imaging, and careful monitoring of the comet's behaviour had to pause while Earth's line of sight to Three-Eye Atlas passed directly through our star. Those 2 weeks felt longer than the previous 4 months. When the comet emerged from behind the Sun in mid-November, reappearing in the morning sky before dawn for observers in the Northern Hemisphere, it had already begun its outbound journey. The trajectory now pointed away from the Sun, carrying the comet back toward interstellar space, though with one critical waypoint remaining. December brought the comet's closest approach to Earth on the 19th, still a comfortable 1.8 astronomical units distant, but positioned for optimal observation. Ground-based telescopes tracked it through the constellations Virgo and Leo, documenting how the coma evolved, how the jets behaved, whether any new anomalies emerged, and ahead, inexorably approaching the Jupiter encounter on March 16, 2026. 4 months from December to March, 16 weeks, 120 days. The window was closing with mechanical precision, and every spacecraft currently operating in the solar system scrambled to position itself for observation, to contribute whatever data its instruments could provide during the brief hours when an interstellar comet would pass through the most complex planetary system within reach. Juno orbits Jupiter in a highly elliptical trajectory designed to avoid the most intense radiation, while still collecting data on the planet's atmosphere, magnetosphere, and internal structure. The spacecraft was not built to study comets. Its instruments target Jupiter specifically. Microwave radiometer to probe atmospheric layers, plasma instruments to measure charged particles, magnetometer to map magnetic field structure, camera system to image cloud formations and auroras. But instruments designed for one purpose can often be adapted to another. Mission planners at NASA's Jet Propulsion Laboratory began calculating whether Juno's orbit could be adjusted to optimize comet observations. The spacecraft follows a 53-day orbit around Jupiter, swooping close to the planet during each perigee, then coasting out to distances where the radiation environment becomes more manageable. The March 16th encounter would occur during one of these outbound legs, when Juno sits far from Jupiter but still within the magnetosphere that extends millions of kilometers from the planet. The calculations showed promise. If Juno's orbit required no major adjustments, and it would not, because such adjustments consume fuel the spacecraft needs to maintain its primary mission, then the spacecraft would be positioned to observe the comet from approximately 10 million kilometers distance during closest approach. The plasma instruments could detect charged particles from the comet's ion tail. The magnetometer could measure how the comet's magnetic field, if it possesses one, interacts with Jupiter's magnetosphere. The camera could image the coma and possibly resolve structure in the jets, Europe's Jupiter Icy Moons explorer JUICE, launched in April 2023, was still in transit, using gravity assists from Earth and Venus to build the velocity necessary to reach Jupiter by 2031. But the mission's trajectory brought the spacecraft through the inner solar system in late 2025, and orbital mechanics placed JUICE in position to observe 3I Atlas during early November, just after the comet emerged from behind the Sun. On November 4, 2025, JUICE passed within 64 million kilometers of the comet. The spacecraft activated its cameras, spectrometers, and particle sensors, collecting what data it could despite the challenging thermal conditions. JUICE was using its high-gain antenna as a heat shield during this phase of its journey through the inner solar system, limiting data transmission rates. The observations themselves succeeded, but the data would not reach Earth until February 2026, when the spacecraft could safely deploy its communication systems without risking thermal damage. Those observations remain locked in JUICE's memory banks, waiting. Europa Clipper presented another opportunity. NASA's flagship mission to Europa launched in 2024 and was following its own complex trajectory toward Jupiter, scheduled to arrive in 2030. But mission planners noticed something intriguing in the orbital calculations. Between October 30th and November 6, 2025, Europa Clipper's trajectory would carry the spacecraft directly through the predicted path of 3I Atlas's ion tail. Not close to the comet itself, the spacecraft would be millions of kilometers from the nucleus, but directly downstream in the tail region, where charged particles stream away from the comet, pushed by solar radiation and the solar wind. Clipper carries instruments designed to study Europa's tenuous atmosphere and any particles the Moon ejects into space. Those same instruments could characterize particles from an interstellar comet's tail, measuring their composition, charge states, and velocities. The spacecraft executed the observation program flawlessly. For 1 week, Europa Clipper drifted through a stream of particles that had sublimated from a comet older than the solar system. Particles carrying chemistry forged around another star, now dispersing into the space between planets. The data is still being analysed, but preliminary results confirm detection of the expected ions: carbon dioxide, carbon monoxide, cyanide compounds, and trace amounts of nickel and other metals. Farther from Jupiter, other spacecraft positioned themselves to contribute. The Psyche mission, en route to study a metal-rich asteroid, passed within 45 million kilometers of 3I Atlas on September 4th. Lucy, targeting Jupiter's Trojan asteroids, observed from even greater distance, but with instruments optimized for faint objects. Even the Parker Solar Probe, in its orbit around the Sun, collected data during the perihelion period, when ground-based observation became impossible. All of these observations, all of these spacecraft, all of this coordination serves one purpose: to gather as much information as possible during the brief window when an interstellar object passes through our cosmic neighborhood and intersects our scientific infrastructure. Because once the encounter ends, once the comet accelerates back toward interstellar space, beyond the reach of our sensors and telescopes, the opportunity vanishes forever. This is the arithmetic of astronomical observation. We cannot follow 3I Atlas into the dark. We cannot send a spacecraft to chase it. The velocities required exceed anything our current propulsion systems can achieve, and even if we could match speeds, the years required to reach interstellar space would outlast the mission's lifespans. We get one pass, one flyby, one chance to point our instruments at this visitor and record what we can before it leaves. The March encounter represents the final crucial observation window. After Jupiter, the comet will continue outbound, gradually fading as it recedes from the Sun. By mid-2026, it will dim below the threshold where detailed spectroscopy remains possible. By 2027, only the largest telescopes will detect it at all. By 2028, it will be gone, a faint point of light merging with the background stars, indistinguishable from the thousands of objects that populate the distant solar system. Everything we learn about this comet, we must learn now. Everything we discover about its trajectory, its chemistry, its behaviour, we must discover in these months. The window is not merely closing, it is already more than half shut, and the remaining opening narrows with each passing day. Mission planners understand this urgency in ways the general public cannot. Every scheduling conflict, every instrument calibration, every data transmission delay represents lost opportunity. You cannot reschedule a comet flyby. You cannot ask it to return for a second observation campaign. Nature provides the timeline, and we either meet it or we miss it. So the spacecraft prepare. Juno configures its instruments for comet observations while maintaining its primary Jupiter science program. Europa Clipper continues analysing the ion tail data it collected. JUICE will transmit its November observations in February, adding another piece to the puzzle. And on Earth, telescope time gets allocated, observation schedules get refined, analysts prepare to receive the flood of data that will arrive during and immediately after the March 16th encounter. 120 days became 90, then 60, then fewer. The comet continues outbound at 52 kilometers per second, crossing 4.5 million kilometers every day, closing the distance to Jupiter with the precision of clockwork. The planet waits in its orbit, massive and patient, its magnetosphere already beginning to sense the approaching visitor through subtle disturbances in the charged particle environment. And we watch, knowing that whatever happens during those few hours in March will be all we ever witness of this encounter. One alignment, one ancient traveller, one chance to understand what it means when chemistry from another stellar system intersects with worlds that might already be preparing to receive it. The window is closing, and beyond it lies only questions and interstellar silence. Comets do not travel in perfect Keplerian orbits. Newton's equations describe how gravity alone shapes trajectories, but comets carry their own propulsion systems built from physics rather than engineering. As ice sublimates into gas, molecules escape the nucleus at hundreds of meters per second, carrying momentum. That momentum must be conserved. For every kilogram of gas that jets away from the surface, the nucleus recoils in the opposite direction, producing thrust measured in fractions of millimeters per second squared. This effect is called non-gravitational acceleration. It has been observed in every active comet studied in sufficient detail. The jets create forces too small to perceive directly, but large enough to accumulate over weeks and months, gradually shifting the orbit from the path that gravity alone would dictate. Astronomers account for these forces when predicting where comets will appear in future observations, adding correction terms to the equations that describe how outgassing alters the trajectory. For 3I Atlas, the question was not whether non-gravitational acceleration existed. The comet was clearly active, clearly outgassing, clearly producing jets that would generate thrust. The question was whether that thrust appeared random or directed. The first detection came from ALMA, the Atacama Large Millimeter Array in Chile, which observed the comet near perihelion on October 29, 2025. The telescope measured the comet's position with arc-second precision, comparing the observed location against predictions based purely on gravitational dynamics. The comet appeared 4 arc-seconds displaced in right ascension from where the equations said it should be. 4 arc-seconds sounds negligible. It represents an angular separation barely resolvable to the human eye under perfect conditions, but at the comet's distance during perihelion, 4 arc-seconds translates to tens of thousands of kilometers of spatial displacement. The comet had deviated from its predicted trajectory by amounts that could not be explained by observational error or gravitational perturbations from planets. Orbital analysts at NASA's Jet Propulsion Laboratory received the ALMA data and began calculating what non-gravitational acceleration would be required to produce such deviation. The numbers came back showing radial acceleration away from the Sun of approximately 1/1,000,000th of an astronomical unit per day squared, plus transverse acceleration perpendicular to the Sun's direction at about 1/3 that magnitude. These accelerations are tiny by human standards. If you experienced 1/1,000,000th of an astronomical unit per day squared, you would barely feel it. A gentle push accumulating to mere centimeters per second over hours. But sustained over the weeks between observations, such acceleration compounds. The velocity change integrates. The position shift becomes measurable. The physics of cometary outgassing provides a natural explanation. When gas sublimates from the nucleus surface, it escapes radially outward from the vent locations. If most vents concentrate on the sun-facing hemisphere, as thermal models predict, then most gas escapes away from the sun, creating net thrust in the same direction. This produces radial acceleration that pushes the comet slightly faster along its trajectory, causing it to arrive at future positions ahead of schedule compared to purely gravitational predictions. The transverse component requires more subtle geometry. If the nucleus rotates, and vents are not perfectly aligned with the rotation axis, then the escaping gas carries angular momentum. Some fraction of the thrust vector points perpendicular to the sun line, creating sideways acceleration that curves the trajectory. The magnitude of this effect depends on rotation rate, vent distribution, and sublimation rate, all quantities that remain uncertain for 3i Atlas. Momentum conservation provides a way to estimate mass loss. The thrust force equals the rate of mass ejection multiplied by the ejection velocity. For typical cometary outgassing, molecules escape at thermal speeds around 300 meters per second, the velocity at which water vapor or carbon dioxide molecules move when heated to sublimation temperature. Using this velocity and the measured acceleration, you can calculate how much mass the comet must be losing per second to produce the observed thrust. The calculation suggested 3i Atlas lost at least 10% of its total mass during the perihelion passage, possibly more if the ejection velocity was lower than 300 meters per second. 10% mass loss represents an enormous outgassing rate, enough to create a massive visible coma, a dense cloud of gas and dust extending millions of kilometers from the nucleus. Such a cloud should be obvious in observations during November and December as the comet receded from the Sun and became visible again from Earth. Yet when the comet emerged from behind the solar glare in mid-November, the coma appeared normal. Bright, yes, with a well-defined central condensation and a faint tail, but not dramatically enhanced. Spectroscopic observations detected the expected carbon dioxide emissions, the cyanide bands, the dust continuum, but the gas production rates calculated from these spectra suggested mass loss around 1 to 2%, not 10% or more. The discrepancy troubled analysts. Either the non-gravitational acceleration measurements were incorrect, which seemed unlikely given ALMA's precision, and independent confirmation from other observatories, or the relationship between outgassing rate and thrust was more complex than simple momentum conservation suggested. One possibility involved the geometry of gas release. If material sublimated primarily from narrow vents rather than broad surface areas, the gas could be highly collimated, escaping in tight beams rather than diffuse clouds. Collimated outgassing would produce more thrust per unit mass lost, because all the momentum vectors align rather than cancelling through random directions. This could reduce the required mass loss to match the observed acceleration. Another possibility involved the composition of the escaping material. If the outgassing consisted primarily of volatile molecules like carbon monoxide or molecular hydrogen, rather than water, the thermal velocity would be higher. Lighter molecules move faster at the same temperature. Higher ejection velocity means more momentum transfer per kilogram, again reducing the mass loss needed to produce the thrust. But molecular hydrogen should not be present in significant quantities in a comet formed around another star billions of years ago. Water and carbon dioxide are stable over cosmic timescales. Hydrogen is so light that it escapes gravitational binding even from objects much larger than cometary nuclei. Unless some mechanism generated hydrogen recently, perhaps through chemical reactions driven by solar heating or cosmic ray bombardment during the interstellar journey, the comet should not be outgassing it. The third possibility was the one nobody wanted to write in official papers, but everyone considered privately. What if the thrust was not entirely explained by random sublimation? What if some component of the acceleration represented guidance rather than geology? Guidance does not require intelligence or technology in the sense those words typically imply. Nature provides many examples of self-correcting systems, feedback loops where physical processes adjust themselves to maintain particular states. A simple example: ice sublimating on a spinning nucleus creates torques that can alter the rotation rate, which changes how thermal energy distributes across the surface, which affects where ice sublimates, closing the loop. Over time, such systems can produce behaviours that appear purposeful, even though they emerge purely from physics. But could such feedback produce trajectory correction? Could a comet, through nothing more than the interplay of rotation, sublimation, and orbital mechanics, effectively steer itself towards specific targets? The mathematics says maybe. Consider a nucleus with irregular shape and non-uniform composition, rotating at some rate determined by its formation and subsequent collisional history. As it approaches the Sun, different regions heat up at different times depending on their orientation relative to solar radiation. Ice sublimates preferentially from the warmest regions, creating jets that produce thrust vectors changing direction as the nucleus rotates. The thrust vectors combine to produce net acceleration that depends on the rotation period, the distribution of volatile-rich regions, and the thermal response time of the surface layers. Now add orbital mechanics. The comet follows a hyperbolic trajectory shaped by the Sun's gravity and the initial conditions inherited from its entry into the solar system. The non-gravitational thrust, even if initially random, perturbs this trajectory. Some perturbations are amplified by gravitational interactions with planets encountered along the way. Others are damped. The result is a modified trajectory that differs from the original path in ways determined by when and where the outgassing occurred. If the comet passed through regions where gravitational assists were possible, close encounters with asteroids, passage through resonances with Jupiter's orbit, alignment with the solar system's angular momentum vector, then even random thrust could be preferentially filtered and shaped by dynamics. The trajectories that survive become those that were accidentally optimal, not because they were designed, but because they were selected. This is a form of natural selection operating on orbital mechanics. Most comets entering the solar system on random trajectories quickly leave again, their paths unmodified by chance. But occasionally one arrives with just the right combination of initial velocity, outgassing distribution, and rotation state, such that its random thrusting happens to produce trajectory corrections that keep it in interesting regions longer, or direct it toward massive planets whose gravity can then shape its future path. We might be observing the lone survivor of billions of comets ejected from their birth systems over galactic history, the one whose chaotic outgassing happened to produce effective steering through pure accident. Or we might be observing something that learned, over billions of years of travel through radiation fields and gravitational wells, how to use its own sublimation as propulsion toward destinations rich in the elements and energy sources that comets are built from. The distinction matters philosophically, but not observationally. Both scenarios produce the same data: a comet exhibiting non-gravitational acceleration consistent with natural processes, but aligned with a trajectory that intersects Jupiter. The measurements cannot distinguish between accident and adaptation, between coincidence and control. What they can do is establish bounds: the thrust magnitude, the direction relative to the Sun, the timing of when acceleration occurred. All these can be measured and compared to models. If the thrust appeared random, varying chaotically as the nucleus tumbled through space, that would suggest uncontrolled outgassing. If the thrust showed structure, sustained directions maintained over rotation periods, variations correlated with orbital position, that would suggest something more organized. The data collected so far shows both. The antitail indicates thrust toward the Sun, which is unusual but not unprecedented. The transverse acceleration indicates sideways push perpendicular to the Sun line, which requires specific vent geometry. The overall magnitude falls within the range expected for natural outgassing, but at the high end, requiring either efficient momentum transfer or substantial mass loss. Every measurement fits within the envelope of natural processes, but collectively they sketch a pattern that sits at the edge of what randomness alone should produce. You imagine the comet's nucleus, perhaps 5 kilometers across, tumbling slowly through space as it falls toward the Sun. Jets erupt from surface vents, each one lasting minutes to hours before the vent rotates into shadow and freezes over. The gas escapes, carrying dust grains that scatter sunlight and create the visible coma. The momentum transfer pushes the nucleus fraction by fraction off its gravitational trajectory, accumulating deviations that compound over weeks into measurable position shifts. If this process were entirely chaotic, the thrust direction would wander randomly as different vents activated and deactivated. The net acceleration would average towards zero over time, or at most produce drift in whichever direction happened to have slightly more active vents. Yet the observations show sustained radial and transverse components maintained across the perihelion passage, when outgassing should have been most chaotic. Sustained thrust requires either very specific vent distribution, most vents concentrated in regions that systematically favour particular thrust directions, or very specific rotation, the nucleus oriented such that volatile-rich regions preferentially face directions that produce desired acceleration. Both scenarios are possible, both are rare, and both would be required simultaneously to produce the Jupiter intersecting trajectory while maintaining the observed thrust pattern. The mathematics permits it. Probability allows it. But probability grows thin when too many rare conditions must align perfectly. In 4 months, when the comet passes through Jupiter's magnetosphere, the non-gravitational acceleration will still be operating, still producing thrust, still modifying the trajectory in ways that depend on where and how gas escapes. If that thrust happens to align such that the encounter distance is maintained or optimized, such that the flyby threading Jupiter's moons becomes more precise rather than less, then the mathematics of steering will face another test, and we will watch, measuring every arc-second of deviation, every spectral line indicating outgassing, every subtle shift in coma brightness that might reveal how this ancient traveller guides itself through the dark. Every comet carries a chemical fingerprint from its birthplace. The ratios of elements, the abundances of isotopes, the presence or absence of particular molecules, all these reveal the conditions under which the comet formed, the temperature and pressure of the protoplanetary disk, the chemistry of the star around which it condensed. Spectroscopy decodes these fingerprints, breaking starlight into wavelengths that map to specific atomic and molecular transitions, allowing us to read composition from photons that have travelled across the solar system. 3I Atlas's spectrum does not make sense. The first oddity was the carbon dioxide dominance. Solar system comets typically show water as the primary volatile, comprising 70 to 80% of the outgassing by mass. Carbon dioxide appears as a minor component, usually less than 20%, sometimes barely detectable. This ratio reflects how water ice dominates the outer regions of stellar systems where comets form, temperatures cold enough that water freezes but warm enough that more volatile species like carbon monoxide have already escaped. 3I Atlas reverses this pattern. Webb's near-infrared spectrograph measured carbon dioxide emissions far stronger than water vapour lines, suggesting the comet is only 4% water by mass. The remaining composition appears dominated by carbon dioxide with additional carbon monoxide, creating a chemistry more typical of objects formed in colder environments or around stars with unusual elemental abundances. This could be explained. If the comet formed farther from its parent star than typical solar system comets, or if that star was smaller and cooler than our Sun, then carbon-rich ices would freeze preferentially, building a nucleus with inverted volatile ratios. Red dwarf stars, which comprise 70% of stellar populations, burn cooler than Sun-like stars and might produce planetary systems where carbon dioxide outcompetes water in the condensation sequence. But the carbon dioxide dominance represents only the beginning of the chemical mystery. Nickel appeared in the spectra with abundances that violated astrophysical expectations. Spectral analysis detected strong nickel emission lines in the coma, indicating the comet was outgassing nickel-bearing molecules or vaporizing nickel-rich dust grains as it heated. Nickel itself is not unusual. Many comets contain trace metals, but the abundance ratio troubled spectroscopists immediately. In typical cosmic material, nickel and iron appear together in roughly comparable amounts, reflecting their formation in supernova nucleosynthesis and their cosmic abundance ratio of approximately 1 nickel atom for every 15 iron atoms. Comets should show this ratio or something close to it, since they formed from the same stellar debris that built planets and stars. Yet 3I Atlas showed nickel far exceeding iron, inverted from cosmic norms by orders of magnitude. One astronomer calculated the nickel to cyanide ratio and found it exceeded any previously measured comet, including 2I Borisov, by factors approaching 100. Cyanide serves as a useful reference because it appears in nearly all active comets, and represents carbon-nitrogen chemistry expected in cold protoplanetary environments. The fact that nickel outweighed cyanide by such margins suggested either extraordinary nickel enrichment or extraordinary cyanide depletion, neither of which fit standard formation models. Nickel concentrates in planetary cores during differentiation. When rocky planets form and heat through gravitational compression and radioactive decay, iron and nickel melt and sink toward the center, leaving lighter silicates in the mantle and crust. This process explains why Earth's core is iron-nickel alloy, while the surface is silicon-oxygen compounds. But comets form in the cold outer regions of stellar systems, never experiencing temperatures high enough for differentiation. They should sample the average composition of the protoplanetary disk, not the core composition of a differentiated body. The nickel enrichment suggested 3I Atlas might be a fragment of a destroyed planet, perhaps a chunk of core material ejected during a catastrophic collision billions of years ago. This scenario had precedent. The solar system contains metal-rich asteroids believed to be fragments of differentiated planetesimals shattered in the asteroid belt. But core fragments should be solid metal, not ice-rich bodies that outgas like comets. And they should show iron in proportions matching nickel, not the inverted ratio observed, unless the parent body differentiated in unusual ways, perhaps around a star with non-standard elemental abundances, or perhaps subjected to chemical processes during destruction that selectively removed iron while preserving nickel. Both possibilities required specific conditions uncommon in typical stellar systems. The spectra revealed other anomalies layered beneath the major ones. The presence of carbon monoxide at concentrations suggesting formation temperatures below 50 Kelvin, meaning the comet condensed in regions colder than Neptune's orbit in our solar system. The absence of certain silicate dust features expected from warm comets, suggesting either unusual dust composition or grain sizes that scatter light differently than normal cometary dust. The detection of organic molecules more complex than simple cyanides, hinting at carbon chemistry more elaborate than standard comet models predict. One particularly intriguing detection involved nickel carbonyl, a molecule consisting of one nickel atom bound to 4 carbon monoxide molecules. This compound forms naturally when nickel metal contacts carbon monoxide at specific temperatures and pressures, but it's extraordinarily toxic and unstable under most conditions. On Earth, it appears primarily in industrial processes where it's synthesized deliberately for nickel purification. Finding it in a comet from another stellar system raised immediate questions about formation mechanisms. Could nickel carbonyl form naturally in interstellar space? The chemistry permits it if nickel atoms and carbon monoxide molecules meet in cold, dense clouds at temperatures around 50 to 100 Kelvin. Cosmic rays provide the energy to overcome activation barriers, and the long timescales of interstellar chemistry allow even slow reactions to proceed to completion. Over billions of years, a comet drifting through molecular clouds might accumulate significant amounts of exotic molecules simply through radiation-driven synthesis, or the molecule might form during the comet's approach to the Sun, when heating liberates nickel from dust grains simultaneously as carbon monoxide sublimates from ice, allowing them to react in the coma. This process would create nickel carbonyl not as a primordial component, but as a secondary product of solar heating, telling us less about the comet's origin and more about its current chemistry. The distinction mattered because it determined whether the anomalous chemistry originated in another stellar system or developed during billions of years of interstellar travel. If primordial, the chemistry revealed the conditions around the comet's birth star. If acquired, it revealed the conditions between stars and the transformative effects of cosmic radiation on ice and rock over galactic timescales. Spectroscopists debated these possibilities in papers and conference calls, proposing mechanisms and countermechanisms, citing laboratory studies of icy radiation and stellar nucleosynthesis yields. Every measurement had error bars. Every detection had alternative interpretations. The spectrum could be fit with models assuming unusual but natural formation conditions, or it could be fit with models assuming standard formation followed by extensive processing. But fitting the spectrum required assumptions, and those assumptions accumulated. To explain the carbon dioxide dominance, assume formation around a cool star. To explain the nickel enrichment, assume origin in a differentiated parent body. To explain the nickel carbonyl, assume either primordial synthesis or solar heating reactions. To explain the low water content, assume selective loss during interstellar travel or formation in unusually cold regions. Each assumption individually was defensible. Collectively, they sketched a formation history unlike any comet we had studied before. You examine the spectral lines on the monitor, each peak and valley representing a different molecule caught in the act of scattering starlight. The carbon dioxide band at 4 microns, the carbon monoxide feature at 2 microns, the nickel emission at 3000 angstroms, the cyanide bands in the visible spectrum. Each line confirmed through multiple observations, each detection verified by different instruments and different teams, building confidence that the chemistry was real even if the interpretation remained uncertain. Comets from our solar system show consistent patterns. Water dominates. Silicate dust appears in expected proportions. Metals appear in cosmic abundance ratios. Organic molecules cluster around simple compounds like methane, ammonia, formaldehyde. The chemistry makes sense because we understand where these comets formed, how they evolved, what processes shape their composition over 4.5 billion years. 3I Atlas's chemistry makes less sense not because it violates physics, but because it requires too many exceptional circumstances. The inverted carbon dioxide to water ratio, the nickel enrichment without corresponding iron, the presence of molecules that should be rare, the absence of features that should be common. Any single anomaly could be natural. The combination stretches natural explanation to include increasingly specific scenarios. This is the pattern that troubles scientists when discussing the comet in private conversations, away from press releases and official statements. Not that anything is definitively artificial, not that any measurement screams manufactured, but that the chemistry occupies a narrow space in the landscape of possibilities, a space that requires just the right stellar environment, just the right formation conditions, just the right processing history to produce what we observe. And that space happens to align with a trajectory that targets Jupiter. Chemistry and trajectory are independent. The molecules in the comet formed billions of years ago, determined by conditions in a stellar system now dead or transformed beyond recognition. The trajectory was set when gravitational forces ejected the comet into interstellar space, shaped by encounters with molecular clouds and stellar gravity wells during millions or billions of years of travel. The two should not correlate, yet both appear optimized for encountering a giant planet with potentially habitable moons. The trajectory threads the needle to Jupiter. The chemistry carries compounds that could catalyze reactions in subsurface oceans, providing elements like nickel that are scarce in water worlds, but essential for certain metabolic processes, delivering carbon molecules more complex than simple dioxide or monoxide, potentially seeding chemistry that the Jovian system cannot produce on its own. If you wanted to design a delivery system for interstellar panspermia, for spreading chemical complexity from one stellar system to another, this is close to what you would create. Not a spacecraft with engines and navigation, not a probe with instruments and transmitters, but a comet, indistinguishable from natural objects except for subtle chemical signatures, following a trajectory that appears gravitational except for barely detectable guidance, carrying cargo that looks like formation artifacts except for their unusual abundances. The design would be elegant. No moving parts to fail over billion-year journeys, no power source to deplete, no communication system to maintain, just ice and rock and chemistry, using gravity and radiation and thermal energy to guide itself toward targets rich in the prerequisites for biology, delivering its cargo through nothing more sophisticated than collision and sublimation. Such a system could operate across galactic scales, dispersing from stellar systems during their death throes, drifting through the void until chance and subtle steering bring them to younger systems, depositing molecules that might catalyze or accelerate the emergence of complexity in worlds not quite ready to produce it themselves. This is speculation layered on uncertainty. Pattern recognition searching for meaning in data that might contain none. The chemistry could be coincidence. The trajectory could be chance. The correlation could be the human mind's tendency to find connections in randomness, to see purpose where only physics operates. But the spectrum persists. The nickel glows in wavelengths that should not be so bright. The carbon dioxide dominates where water should rule. The molecules appear that should be rare. And in 4 months, all of this chemistry will pass through the Jupiter system, mixing with whatever processes are already unfolding in those buried oceans, adding complexity that might matter or might dissolve into irrelevance. We measure, we analyze, we build models and compare them to observations, and the chemistry continues not making sense in ways that are individually explicable, but collectively unsettling, as if something, somewhere, long ago understood that life needs more than water and time. It needs chemistry, and chemistry sometimes needs delivery. The ice hides everything. For billions of years, Europa's frozen shell has concealed what moves beneath, preserving whatever chemistry unfolds in darkness far from sunlight. The surface temperature hovers around -160 degrees Celsius, cold enough to turn carbon dioxide into frost, cold enough the water ice behaves like granite, fracturing and cracking under tidal stress rather than flowing. But 15 kilometers below that frozen surface, pressure and tidal heating maintain liquid water in quantities that dwarf Earth's oceans. This is not a sterile ocean. It is a laboratory where chemistry has been operating for 4 billion years, continuously, without pause, driven by energy sources that never deplete. Tidal forces generate the warmth. As Europa orbits Jupiter in gravitational lockstep with Io and Ganymede, the 3 moons create a resonance that flexes Europa's interior. The ice shell rises and falls by tens of meters during each orbit, bending and stretching the moon's interior, converting gravitational energy into heat through friction. This heat prevents the ocean from freezing and likely drives convection currents that transport material between the seafloor and the ice above. The seafloor itself represents a critical interface. Europa's rocky mantle directly contacts the ocean, allowing water to interact with silicate minerals at temperatures warm enough for chemistry to proceed. On Earth, similar environments host hydrothermal vents, where superheated water enriched with minerals erupts from cracks in the seafloor. Life thrives at these vents. Chemosynthetic bacteria harvesting energy from hydrogen sulfide and methane rather than sunlight, forming the base of ecosystems that include tube worms, crabs, and complex microbial mats. Europa may possess similar vents. The tidal heating that keeps the ocean liquid also generates geological activity in the rocky core. Pressure and temperature conditions at the ocean rock boundary mirror those at Earth's mid-ocean ridges. If water circulates through fractures in the rock, gets heated, reacts with minerals, and erupts back into the ocean, then Europa has access to the same chemistry that supports life in Earth's deep oceans. The ingredients exist. Water is abundant. Energy flows continuously from tidal forces. Organic molecules have been detected on the surface, where radiation processing breaks down complex compounds into simpler radicals that could recombine in different forms in the ocean below. Salts appear in surface spectra, suggesting the ocean is electrically conductive, capable of sustaining electrochemical gradients. Hydrogen should be produced at the rock-water interface through serpentinization reactions, where water splits iron-bearing minerals. What is missing is delivery. Europa's ice shell isolates the ocean from space. Material from outside reaches the surface but rarely penetrates to the water below. The geological processes that might transport surface compounds downward operate on timescales of millions of years, too slow to provide rapid influx of new chemistry. The ocean must work with whatever elements and molecules it inherited from Europa's formation, plus whatever can be extracted from the rock below. This limitation constrains what complexity the ocean can achieve. Biology requires not just the common elements, carbon, hydrogen, oxygen, nitrogen, but also trace metals that serve as catalysts in enzymatic reactions. Nickel, for instance, is essential for methanogenesis, the metabolic pathway where archaea produce methane from carbon dioxide and hydrogen. Cobalt enables certain vitamin synthesis pathways. Molybdenum participates in nitrogen fixation. On Earth, these metals are scarce in seawater, but concentrated at hydrothermal vents where they leach from rock. Europa's vents might provide similar enrichment, but the availability depends on the mineral composition of the rocky mantle, which in turn depends on the conditions under which Europa formed. If the Moon condensed from material depleted in certain elements, or if the differentiation process sequestered metals in the deep interior, then the ocean might lack catalytically important trace elements. An interstellar delivery could change this equation. When 3I Atlas passes through the Jupiter system in March, some fraction of its material will be gravitationally captured. Dust grains will spiral slowly inward over months or years, some impacting Europa's surface. The material will be processed by radiation, bombarded by charged particles in Jupiter's magnetosphere, chemically altered by ultraviolet light. But beneath these transformations, the core composition remains: nickel-rich chemistry from another stellar system. Organic molecules synthesized over billions of years in interstellar space, compounds that do not naturally occur in the Jovian system. If even a kilogram of this material eventually reaches Europa's ocean, transported through cracks, carried by cryovolcanic flows, dissolved in liquid pockets within the ice, it introduces chemistry the Moon cannot produce on its own, not life itself, not even necessarily the direct precursors to life, but catalysts, cofactors, molecules that enable reactions previously too slow or too energetically unfavourable to proceed. Ganymede orbits farther out, larger than Mercury. the only moon in the solar system with its own magnetic field. The magnetosphere shapes how charged particles from Jupiter's radiation belts interact with the surface, creating auroras at the poles, channeling energy into the upper atmosphere in ways that drive complex atmospheric chemistry. But the real story lies deeper, beneath 150 kilometers of ice, where magnetic field measurements suggest a salty ocean persists. This ocean is different from Europa's. Thicker ice means less exchange with the surface, reduced likelihood of material transport between worlds. The burial provides stability. The ocean is protected from Jupiter's intense radiation, shielded from the bombardment that erodes surface features on less protected moons. But it also means isolation. Whatever chemistry unfolds in Ganymede's depths operates with limited access to external input. The moon's internal structure adds complexity. Unlike Europa, where the ocean probably contacts rock directly, Ganymede may possess multiple ice layers of different crystalline structures, with the liquid ocean sandwiched between high-pressure ice phases. This geometry prevents or severely limits water-rock interaction. The ocean might receive no fresh minerals from below, no hydrogen from serpentinization, no chemical influx beyond what dissolved in the water when Ganymede formed. Such an ocean would be thermodynamically dead. Without energy gradients, without chemical disequilibrium to harvest, metabolism becomes impossible. Life requires fuel, and fuel requires chemistry that wants to react but needs a catalyst or pathway to proceed. An isolated ocean in equilibrium with its surroundings contains no such fuel. Yet Ganymede is geologically active in ways that remain poorly understood. The surface shows evidence of tectonic processes, vast grooved terrains where the ice crust fractured and reformed, possibly driven by tidal heating from orbital resonances or internal convection. If the surface can move, can crack, can allow exchange between layers, then perhaps the ocean is not entirely isolated. Perhaps pathways exist for material to descend from the surface or ascend from the rocky core, maintaining the chemical gradients that metabolism requires. An interstellar delivery reaching Ganymede would face the challenge of penetrating 150 kilometers of ice. Direct transport seems implausible on human timescales, but ice is not static. It flows under pressure, convects under temperature gradients, fractures under stress. Over millions of years, surface material works its way down through crystalline phase transitions and slow diffusion. A delivery today might reach the ocean in 1 million years, introducing chemistry on geological timescales rather than biological ones. This is patience operating at the pace of planets. The comet does not deliver immediately, it delivers inevitably. Callisto occupies the safest orbit, far enough from Jupiter that tidal heating barely affects its interior, far enough that radiation levels drop to manageable intensity. The surface preserves 4.5 billion years of history, every impact crater still visible. No geological processes erasing the record of ancient bombardment. This moon is the archive, the keeper of memory, the witness to everything that has happened since the solar system formed. Yet even Callisto may hide liquid water. Magnetic field measurements during Galileo spacecraft flybys detected induced fields, suggesting electrically conductive layers at depth. The most plausible explanation is a subsurface ocean kept liquid not by tidal heating but by residual heat from radioactive decay and formation processes. Ammonia mixed with water lowers the freezing point, allowing liquid to persist at temperatures that would otherwise produce only ice. This would be the coldest, oldest, most isolated ocean in the Jovian system. No tidal energy driving circulation, No geological activity renewing chemistry. Just water sitting in darkness, heated by the faint glow of uranium and thorium decay in the rocky interior, barely liquid, barely active, persisting through patience alone. Life in such an environment would need to operate at minimum metabolism, reactions proceeding so slowly that generations might span millennia. But slow does not mean impossible. Chemistry continues at low temperatures, just at reduced rates. Given enough time, and Callisto has had billions of years, even the slowest reactions accumulate products. Even the most improbable events eventually occur. An interstellar delivery to Callisto's surface would be preserved indefinitely. No geological activity to erase it, no weathering to erode it, just ice accumulating layer upon layer, burying the deposit under meters of new frost, maintaining it in frozen stasis until distant epochs when future beings might excavate and discover evidence that once, billions of years ago, chemistry from another star system touched this ancient world. The 3 ocean moons form a gradient of accessibility and isolation. Europa is active, exchanging material between ocean and surface on relatively rapid timescales, but exposed to intense radiation. Ganymede is protected but buried, isolated beneath thick ice that prevents easy exchange. Callisto is ancient and cold, barely active but stable over geological time. Together they represent 3 experiments in how life might emerge or persist in radically different environments. 3 laboratories testing whether biology requires sunlight and warmth, or whether it can operate in darkness and cold given sufficient time and the right chemistry. When 3i Atlas delivers its cargo, when dust and molecules and complex chemistry from another stellar system rains down on these worlds, each moon will respond according to its nature. Europa will transport some fraction to its active ocean, within thousands to millions of years. Ganymede will store the material in its ice, slowly transporting it downward over geological epochs. Callisto will preserve it on the surface, a time capsule within a time capsule. And in one of these oceans, or all of them or none, chemistry will continue. Molecules will combine and recombine, driven by available energy, constrained by thermodynamics, exploring the space of possible reactions. The addition of new compounds from interstellar sources will not create life directly, but it might provide the final catalyst, the missing element, the enabling cofactor that allows reactions previously impossible to proceed. You cannot see these oceans. They hide beneath kilometers of ice, inaccessible to direct observation, revealed only through magnetic field measurements and tidal modeling and spectroscopic analysis of surface features. But knowing they exist changes how you interpret the comet's approach. This is not a rock visiting a planet. This is chemistry from one stellar system encountering potentially living worlds in another, possibly delivering compounds that took billions of years to synthesize, delivering them to environments that might be preparing to use them. The ice hides everything, but soon, very soon, it will receive something from beyond. And what happens then depends on whether these oceans are empty laboratories waiting for reagents, or active systems ready to incorporate new chemistry into processes already unfolding in the dark. The idea has ancient roots. Greek philosophers proposed that life exists throughout the cosmos, scattered like seeds across the void. In the 19th century, scientists suggested microorganisms might travel between planets aboard meteorites. By the 20th century, Francis Crick and Leslie Orgel formalized the concept into what they called directed panspermia, the deliberate seeding of lifeless worlds by intelligent civilizations seeking to propagate biology beyond their own stellar systems. The hypothesis was always controversial. It addresses one mystery, the origin of life, by invoking another, the existence of prior civilizations capable of interstellar engineering. Most scientists rejected it, not because the physics was impossible, but because the premise seemed unnecessary. Life could originate through chemistry alone, given time and the right conditions. Why invoke intelligence when molecules and energy suffice? Yet the hypothesis never quite disappeared. It lingered in the scientific literature, occasionally surfacing in papers exploring mechanisms for interstellar transport of organic material, ethical frameworks for humanity's own potential role in cosmic seeding, mathematical models of how life might spread through galaxies over billions of years. And occasionally, when unusual objects entered our solar system from interstellar space, the hypothesis emerged again in whispered conversations that rarely made it into official publications. 3i Atlas has revived those whispers. The pattern troubles people. Not any single element, anomalous chemistry can be explained. Precise trajectories can be coincidental. Non-gravitational acceleration is standard for comets. But the combination creates unease, the sense that too many unlikely factors align simultaneously. An interstellar object arriving from the direction of the galactic center, chemistry enriched in metals like nickel that serve as cofactors in certain metabolic pathways, a trajectory that threads through the solar system to encounter Jupiter, the planet whose moons offer the most promising environments for subsurface oceans. Sustained outgassing that might constitute guidance, or might be random, but happens to maintain the encounter geometry. If you were designing a system for interstellar panspermia, this approximates what you would create. Not a spacecraft with engines and computers, too complex, too fragile, too dependent on technologies that might fail over billion-year transit times, but a comet indistinguishable from natural objects except for subtle signatures, ice and rock providing radiation shielding for organic cargo, gravity and sublimation providing navigation without active control, chemistry providing the payload, molecules that catalyze reactions or enable pathways unavailable to the receiving system. The elegance lies in the simplicity. A civilization facing extinction from their star's death throes could eject millions of comets from their system, each one carrying samples of their biochemistry frozen in ice. Most would miss any targets, drifting through interstellar space indefinitely. But with millions of attempts across millions of years, some would inevitably encounter younger stellar systems, and of those, some fraction would pass near planets or moons with conditions suitable for life. No communication required, no monitoring, no complex artificial intelligence maintaining systems over cosmic time, just basic physics, gravity to guide the trajectory, sublimation to adjust the path as the comet warms, eventual delivery to worlds where the chemistry might matter. The system operates entirely through natural processes, requires no technology beyond the ability to launch objects to escape velocity, and succeeds if even one comet in a billion finds a habitable target. This is the hypothesis that scientists discuss in private but rarely publish. It fits the observations, it explains the anomalies, it provides motivation for the trajectory and purpose for the chemistry. But it also requires accepting that we live in a universe where intelligent life has existed before us, where civilizations have developed methods for propagating biology across interstellar distances, where Earth or the Jovian system might be receiving such a delivery right now. the evidence remains circumstantial. Every measurement has natural explanations. Every anomaly can be fit with models that invoke unusual but permitted conditions. The nickel enrichment might reflect formation around a metal-rich star. The carbon dioxide dominance might indicate condensation in cold regions. The Jupiter trajectory might be statistical chance. The non-gravitational acceleration might be random outgassing that happens to produce sustained thrust in useful directions, but circumstantial evidence accumulates. Oumuamua, the first detected interstellar object, showed acceleration without visible outgassing, an elongated shape inconsistent with natural comets, and a trajectory that suggested control, even if the mechanism remained unclear. 2I Borisov behaved more like a standard comet, but still carried chemistry distinct from solar system objects. Now 3I Atlas arrives with its own suite of anomalies, different from its predecessors but equally puzzling. 3 interstellar visitors, 3 different sets of unusual properties, 3 trajectories that, while natural under gravitational dynamics, each selected interesting targets within our solar system. Oumuamua passed near Earth's orbit. Borisov approached the Sun for detailed observation. Atlas aims at Jupiter's potentially habitable moons. If these are natural objects, we're observing the diversity of cometary properties across stellar systems, each one reflecting different formation conditions, different stellar environments, different evolutionary histories. The variety teaches us about planet formation in other stellar systems, about how interstellar radiation processes material over billions of years, about the chemistry that emerges in regions of the galaxy we cannot directly observe. If they are not entirely natural, if some component of design influences their trajectories or chemistry or behavior, then we are observing a galactic-scale system for propagating life, one that operates through physics rather than engineering, that requires no active guidance yet produces targeted delivery, that preserves cargo across billions of years of transit while maintaining readiness to deploy when suitable targets appear. The hypothesis cannot be tested with current observations. Nothing in the data definitively separates natural from designed. The chemistry is unusual but not impossible. The trajectory is precise but not inexplicable. The behavior is anomalous but not artificial. We lack the resolution to detect deliberate patterns, the context to recognize intentional versus accidental, the knowledge to distinguish optimization from coincidence. Yet the hypothesis provides predictions. If 3I Atlas represents directed panspermia, then its encounter with Jupiter should show further signs of optimization. The flyby distance might adjust to maximize material capture by the moons. The outgassing might increase during the encounter, enhancing delivery. The chemistry might show additional anomalies that make sense only in the context of biological utility. Molecules specifically useful for catalyzing reactions in subsurface oceans. Elemental ratios optimized for metabolic pathways. Organic complexity beyond what interstellar radiation alone produces. If we observe these signatures, the hypothesis becomes more plausible. If we observe random behavior, pure physics with no hint of purpose, then the hypothesis retreats to coincidence, and we continue cataloguing unusual natural objects. Either outcome advances knowledge. Finding evidence of directed panspermia would revolutionize our understanding of life's distribution in the universe, confirm that intelligent civilizations have existed long enough to develop interstellar seeding capabilities, provide templates for humanity's own potential role in propagating biology. Finding purely natural explanations would constrain theories of cometary behavior, refine models of stellar system formation, demonstrate the diversity of chemistry that emerges in different galactic environments, the discomfort comes from uncertainty. We have 3 data points, 3 interstellar visitors, 3 sets of anomalies. Not enough to establish patterns with confidence, not few enough to dismiss as random, just enough to suggest possibilities without confirming them, to raise questions without providing answers, to indicate that the universe might operate according to principles we have not yet recognized. Scientists live with uncertainty. It is the natural state of investigation, the gap between observation and explanation that research gradually fills. But this particular uncertainty carries weight beyond typical scientific puzzles. If the hypothesis has merit, if directed panspermia operates as a galactic mechanism, then humanity's emergence occurred in a universe already seeded, already carrying biological heritage from civilizations that died before our sun ignited. We would be recipients of an inheritance we never knew existed, beneficiaries of delivery systems operating for so long that their designers have been forgotten, part of a biological lineage extending not just to Earth's last universal, common ancestor, but potentially to life that emerged billions of years earlier around stars that no longer exist. The hypothesis also carries implications for humanity's future. If life spreads through galaxies via directed panspermia, if this represents a strategy that intelligent civilizations adopt when facing extinction, then we face an eventual choice. Do we propagate our own biological heritage when our sun begins its death? Do we design our own comets, our own delivery systems, our own chemistry to seed younger worlds millions of years hence? Do we participate in the galactic cycle of life spreading from old systems to new ones, continuing the process that might have delivered organic complexity to our own planet? These are questions for distant futures, for times when humanity commands resources sufficient for interstellar engineering. But they begin with observations happening now, with telescopes tracking an ancient comet as it approaches Jupiter, with spectrometers measuring chemistry that makes slightly less sense than it should, with orbital analysts noting trajectories that work too well to be entirely comfortable with calling them random. The hypothesis nobody wants to say aloud persists because we cannot yet disprove it, and because 4 months from now, when the comet passes through the Jupiter system, when it delivers whatever cargo it carries to moons that might already be preparing to receive it, we will collect the data that either strengthens or weakens the pattern we're beginning to perceive. We watch, we measure, we remain agnostic between possibilities, and somewhere in the back of our minds we wonder whether this ancient traveller knows something about the universe that we're only beginning to suspect. March 16, 2026 will arrive regardless of our readiness. The comet does not wait for complete observation plans, for instruments to be calibrated, for teams to coordinate. It follows its trajectory with mechanical precision, closing the distance to Jupiter at 52 kilometers per second, each day consuming another 4.5 million kilometers of space between present position and final encounter. The observation strategy must account for what we can measure and what remains beyond our instrument's capabilities. We cannot send a spacecraft to intercept the comet. The velocities required exceed our propulsion technologies, and the timeline allows no margin for mission planning and launch. We cannot divert the comet or influence its path. It carries too much momentum, moves too fast, exists too far from Earth for any intervention to reach it in time. We can only observe from distance, using whatever tools happen to be positioned correctly when the moment arrives. Those tools represent decades of investment in planetary science. Juno orbiting Jupiter was designed to study the giant planet's atmosphere, magnetosphere, and internal structure. Its instruments were optimized for Jupiter, not comets. But instruments measure electromagnetic radiation and charged particles, and both phenomena will appear during the encounter regardless of their source. The spacecraft can be repurposed, at least partially, to collect data on how an interstellar comet interacts with the magnetosphere 10 million kilometers across. The Juno spacecraft follows an elliptical orbit that brings it close to Jupiter every 53 days, swooping through intense radiation belts during each perigee, before climbing back to safer distances where electronics survive longer and observation continues without constant bombardment. The March encounter timing places Juno approximately 10 million kilometers from the comet during closest approach, distant but within range of several instruments. The magnetometer will measure magnetic field perturbations as the comet's ion tail interacts with Jupiter's magnetosphere. Every charged particle streaming away from the comet creates tiny currents, minute disturbances in the field lines that wrap around Jupiter. The magnetometer is sensitive enough to detect these disturbances, to map how the comet's plasma integrates with Jupiter's, to reveal whether the interaction follows expected physics or displays anomalies. The plasma instruments will count ions directly, measuring their velocity, charge state composition. When the comet's outgassing creates charged particles through ionization, by solar radiation, and Jupiter's energetic particle environment, those ions will stream along magnetic field lines. Some will spiral inward toward Jupiter, others outward toward interstellar space. The plasma detectors will sample whichever populations cross Juno's path, providing direct chemistry measurements of what the comet releases into the Jovian system. The camera system, JunoCam, was designed for public outreach more than serious science, but it can still image the comet if the brightness exceeds threshold limits and the pointing can be adjusted appropriately. High-resolution photographs will reveal coma structure, jet morphology, changes in activity level. The images will not match Hubble's quality, but they will provide unique perspective from within Jupiter's magnetosphere, from angles no Earth-based telescope can achieve. Ground-based observatories represent the other major component of the observation network. Every major telescope with access to the sky during the encounter has allocated time. Mauna Kea in Hawaii, Cerro Paranal in Chile, the Canary Islands, South Africa. All the premier observation sites will turn their instruments toward Jupiter on March 16th, and the days surrounding it, tracking the comet as it threads through the moon system, monitoring for any changes in behavior that might indicate the encounter is more than a simple flyby. Spectroscopy will run continuously. Every major spectroscopic facility will collect data measuring which molecules the comet outgasses, whether the chemistry changes as Jupiter's radiation environment processes the material, whether new compounds appear that were not present earlier. The nickel signatures will receive special attention. If the abundance increases during the encounter, that would suggest liberation of previously buried material. If it decreases, that might indicate depletion through loss to space or capture by Jupiter's magnetosphere. Webb will observe in the infrared, seeing through dust that obscures visible light, detecting thermal emission from the nucleus and coma. The temperature of the outgassing material reveals information about the energy driving sublimation, about whether the heating is purely solar or includes other sources. Anomalous temperatures might indicate internal heat, chemistry releasing energy, processes beyond simple ice sublimation. Hubble will provide visible light imaging with resolution ground-based telescopes cannot match. The aging observatory has observed 3I Atlas before, and will observe it again during the encounter, documenting how the coma evolves, whether jets change direction or intensity, whether the comet fragments under tidal stress from Jupiter's gravity or remains intact. Radio telescopes will listen for any electromagnetic emission beyond what natural plasma processes produce. Charged particles spiraling along magnetic field lines emit radio waves through synchrotron radiation. The intensity and frequency spectrum of that emission depends on particle energies and magnetic field strength. Anomalous radio signatures might indicate particle acceleration beyond what Jupiter's magnetosphere normally produces, or unusual magnetic field configurations around the comet nucleus. The outcomes range across a spectrum of possibilities. At one extreme lies the scenario where nothing unusual occurs. The comet passes Jupiter, gravitational dynamics proceed as calculated, the material outgassed during the encounter disperses into space or impacts Jupiter's atmosphere. The moons receive trace amounts of dust and molecules through random processes, and the event concludes as an interesting but ultimately routine astronomical observation. This outcome would confirm that 3I Atlas, despite its anomalies, behaves fundamentally like a natural comet. The chemistry might remain unusual, the trajectory might remain improbably precise, but the encounter itself would demonstrate that no guidance operates, no optimization occurs, no purpose drives the flyby beyond physics. At the other extreme lies discovery of clear optimization. The comet adjusts its trajectory during the encounter, using outgassing to fine-tune the flyby distance. The chemistry shifts to maximize delivery of certain compounds to the moons. The activity level increases precisely when material would most effectively be captured by Europa's or Ganymede's gravity wells. The behavior shows patterns that natural processes cannot easily explain, signatures that suggest intention. This outcome would force reconsideration of everything. Natural explanations might still exist. Perhaps feedback between sublimation and rotation creates self-correcting systems. Perhaps the chemistry responds to Jupiter's radiation environment in ways we have not anticipated. Perhaps the patterns are coincidence magnified by our desire to find meaning. But such patterns would demand investigation beyond what we can provide with current observations, would require missions to rendezvous with future interstellar visitors, would transform directed panspermia from speculation to testable hypothesis. Between these extremes lies the more probable outcome: ambiguity. The comet will behave mostly as physics predicts, but with subtle deviations. The chemistry will show changes, but whether those changes represent natural responses to new environments or evidence of optimization will remain unclear. The trajectory will pass close to the moons, but whether that represents chance or targeting will depend on statistical interpretations that different analysts will evaluate differently. Science advances through such ambiguity. Each observation constrains possibility space. Each measurement reduces the range of viable explanations. Each encounter with strange phenomena teaches us what questions to ask next time. Even if the March encounter does not definitively answer whether 3I Atlas represents natural or designed delivery, it will provide data for refining both hypotheses, for understanding what signatures we should look for in future interstellar visitors, for building the observational framework that might eventually distinguish accident from intention. The encounter will be brief. The comet moves at 52 kilometers per second relative to Jupiter. The close approach phase, when the comet passes within a few 100,000 kilometers of the moons, will last only hours. The entire time the comet remains in the inner Jovian system, close enough for high-resolution observation, spans perhaps 2 days. Then the comet will accelerate away, climbing back out of Jupiter's gravity well, continuing its journey toward interstellar space. Everything we learn must be learned in that window. Every spectrum captured, every image recorded, every magnetic field measurement logged during those hours represents data we will never have another chance to collect. The comet will not return. No follow-up observations will be possible once it exits the Jovian system. This is our single opportunity to witness how interstellar material interacts with potentially habitable worlds, to observe whether chemistry from one stellar system can integrate with environments in another, to test whether the universe operates seeding mechanisms we've not yet recognized. The teams are ready. Observation schedules have been finalized, instrument parameters optimized, data storage allocated. Everyone involved in the campaign understands the stakes. This is not routine astronomy. This is witnessing an event that might occur only a few times per century. An interstellar object passing through the most astrobiologically interesting region of our solar system, carrying chemistry that might catalyze or contaminate, or simply add complexity to oceans that might already be alive. You imagine standing in the control room when the data begins arriving. First, the magnetometer reading showing field perturbations as the comet enters Jupiter's magnetosphere. Then plasma detections as ions stream along field lines. Then spectroscopic data revealing which molecules are being released, whether the chemistry matches predictions or displays surprises. Then images showing the coma structure, the jet morphology, whether the comet remains intact or begins fragmenting under tidal stress. Each data point will be analysed immediately, compared against models, checked for anomalies. Real-time decisions will be made about whether to adjust observation parameters, to prioritise certain instruments over others, to extend observation campaigns beyond initial allocations. The March encounter is scripted but not rigid. If unexpected phenomena appear, the teams will adapt, pursuing whatever leads emerge, even if that means abandoning pre-planned observations. This is how astronomy operates when confronting the unknown. You prepare for what you expect while remaining ready for what you cannot anticipate. You build models based on current understanding while acknowledging those models might be incomplete. You measure with instruments designed for different purposes, extracting whatever information they can provide even when that information falls short of what you need. And when the encounter ends, when the comet accelerates away from Jupiter carrying with it whatever secrets it retains, you compile the data and begin the analysis that might take months or years to complete. You write papers presenting the findings, proposing interpretations, suggesting what future observations might resolve the ambiguities that remain. You add this encounter to the growing archive of interstellar visitor data, building the statistical sample that might eventually reveal whether these objects represent random debris from stellar systems or something more coordinated. The signs will be in the data. Whether we recognize them depends on whether we know what to look for. Whether we admit what we find depends on how far the evidence pushes us from comfortable natural explanations toward possibilities we have only entertained as speculation. March 16th, 2026. The calendar continues its countdown, and we prepare to watch. Nickel sits at position 28 on the periodic table between cobalt and copper, a transition metal with properties that make it essential for certain forms of life and entirely irrelevant to others. On Earth, nickel appears in trace amounts in seawater, concentrated in hydrothermal vent fluids, and embedded in the iron-nickel core 4,000 kilometers below the surface. Most organisms can survive without it, but some cannot. Methanogenic archaea require nickel for a specific enzyme called methyl coenzyme M reductase. This enzyme catalyzes the final step in methanogenesis, the metabolic pathway that produces methane from carbon dioxide and hydrogen. Without nickel, the enzyme does not function. Without the enzyme, methanogenesis does not proceed. Without methanogenesis, an entire class of organisms that might thrive in Europa's dark ocean cannot exist. The biochemistry is specific. The enzyme uses nickel in a complex called factor F430, where the metal sits at the center of a tetrapyral ring, coordinating with nitrogen atoms that hold it in precise geometry. The nickel cycles between oxidation states during the catalytic cycle, accepting and donating electrons that drive the chemical transformation of methyl groups into methane. No other metal can substitute effectively in this role. Cobalt comes close but does not match nickel's efficiency. Iron, despite being far more abundant cosmically, cannot perform the required chemistry. This specificity means that any environment hoping to support methanogenic life needs bioavailable nickel. On Earth, the metal leaches from basaltic rocks at mid-ocean ridges, where seawater circulates through hot crust and extracts dissolved minerals including nickel sulfides and nickel chlorides. The concentration remains low, but sufficient. Methanogens cluster near hydrothermal vents where the supply is richest, harvesting the metal from vent fluids and incorporating it into their metabolism. Europa's ocean might lack this supply. The Moon formed from material in Jupiter's protoplanetary environment, possibly depleted in certain metals compared to Earth's formation region. If Europa's rocky core contains less nickel than Earth's mantle, if the water-rock interaction at the seafloor does not efficiently extract what nickel exists, then the ocean might be nickel-limited. Chemistry capable of producing methane might exist. Carbon dioxide should be abundant from geological outgassing. Hydrogen should be produced through serpentinization reactions, but the catalytic metal required to complete the pathway might be scarce. An external delivery changes this constraint. When 3 Atlas passes through the Jovian system, some fraction of its nickel-rich material will be gravitationally captured. Dust grains will spiral inward over months, eventually impacting the moons or being captured by Jupiter itself. Molecules containing nickel will disperse through the magnetosphere, some fraction settling onto Europa's surface, where radiation processing and geological activity might eventually transport them to the ocean below. The timescales are long. Surface material requires thousands to millions of years to reach the subsurface ocean through ice convection or cryovolcanic transport. But long timescales are irrelevant on worlds where life, if it exists, has already been waiting for billions of years. What matters is whether the delivery occurs at all, whether chemistry unavailable from local sources eventually reaches environments where it might enable reactions previously impossible. The nickel signature in 3I Atlas's spectrum represents more than an analytical curiosity. It constitutes a potential key, a cofactor that unlocks metabolic pathways, a trace element whose presence or absence determines whether certain forms of biochemistry can emerge. If the comet delivers even small amounts of bioavailable nickel to Europa's ocean, it provides something the Moon might not produce on its own, something that might be the difference between an ocean rich with organic chemistry but devoid of metabolism, and an ocean where energy harvesting through methanogenesis becomes possible. This is not seeding life directly. No organisms travel in the comet's ice, no bacteria frozen in interstellar hibernation ready to awaken when warmed. The delivery is purely chemical. Elements, molecules, compounds that provide raw materials for reactions. Whether those reactions lead to life depends entirely on what chemistry already exists in Europa's ocean. Whether the conditions support self-organization whether the energy gradients are sufficient to drive complexity. But chemistry requires ingredients. A kitchen stocked with flour and water produces only simple mixtures. Add yeast and salt and the range of possibilities expands. The yeast does not create bread. The baker creates bread using the yeast as a tool. Similarly, nickel does not create life. But life, if it emerges, might use nickel as a tool for harvesting energy from available chemical gradients. The spectrum shows nickel at wavelengths corresponding to atomic emission lines, bright features indicating the element is present in gaseous form in the coma, either vaporized directly from the nucleus or released from dust grains heated by sunlight. The intensity of these lines exceeds what cosmic abundance ratios predict. Spectroscopists have measured the line strengths repeatedly, using different instruments, different telescopes, different analysis methods. The result remains consistent. Nickel appears enriched relative to iron by factors of 10 to 100 compared to normal solar system material. This enrichment might be primordial, reflecting the composition of the comet's formation environment. Stars with different metallicities produce planetary systems with different elemental ratios. A star enriched in nickel relative to iron, perhaps because it formed from gas clouds seeded by supernovae with unusual nucleosynthesis yields, would produce comets reflecting that enrichment. The 3T Atlas signature would then tell us about its birth star's chemistry, about conditions in a stellar system that no longer exists or exists too far away to observe directly, or the enrichment might be acquired, the result of processes during billions of years of interstellar travel. Cosmic rays bombard the comet continuously, inducing nuclear reactions that transmute elements, creating isotopes and species not present in the original material. Selective sputtering might remove lighter elements from the surface while heavier metals like nickel remain embedded more deeply. Chemical reactions driven by radiation might create nickel-rich compounds that concentrate in certain layers while other materials sublime away. Or, and this possibility receives less discussion in formal papers, the enrichment might be intentional. If the comet represents a designed delivery system, if directed panspermia operates through chemistry rather than organisms, then the composition would be optimized for biological utility. Nickel would be enriched because nickel enables metabolism. Carbon dioxide would dominate because carbon dioxide provides feedstock for organic synthesis. The molecular complexity would exceed what radiation alone produces because the molecules were selected for their catalytic or structural properties. Testing these alternatives requires understanding not just what is present, but why it is present. Primordial enrichment should show correlation with other elements. If nickel is enriched, certain other metals should be enriched or depleted in predictable patterns based on nucleosynthesis. Acquired enrichment should show isotopic anomalies, signatures of cosmic ray exposure or photochemical processing. Intentional enrichment should show optimization, patterns that make sense from a biological perspective, but seem unlikely from purely geological processes. The data collected so far do not decisively favour any interpretation. The nickel is enriched, the carbon dioxide dominates, the organic complexity exceeds baseline expectations. But each anomaly admits multiple explanations, and the explanations do not yet cohere into a single narrative that accounts for all observations simultaneously. What we know is that in 4 months, this nickel-rich chemistry will pass within 54 million kilometers of Europa. Some fraction will be captured. Some smaller fraction will eventually reach the surface. Some even smaller fraction might, over geological time, reach the ocean. The amount will be tiny measured in human terms, perhaps kilograms, perhaps tons, certainly not enough to change the ocean's bulk composition detectably, but biochemistry operates at molecular scales. Enzymes process individual atoms, catalytic sites bind single metal ions. If even 1 kilogram of bioavailable nickel reaches Europa's ocean and distributes through even a fraction of its volume, that provides sufficient material for billions of organisms to construct billions of enzymes, assuming organisms exist or emerge that can utilize it. This is the leverage that trace elements provide. Not bulk material for building structures, but rare cofactors that enable specific reactions. Not changing the ocean's composition, but changing what chemistry the ocean can perform. Not creating life, but removing a constraint that might prevent life from utilizing available energy gradients. The nickel signature persists in every observation. The lines glow at 3000 angstroms, marking where nickel atoms excited by solar radiation release photons as they decay back to ground state. The brightness varies as the comet rotates, as different regions of the nucleus face the Sun, as sublimation rates change with heliocentric distance. But through all these variations, the enrichment remains. The anomaly that transforms this comet from an interesting natural object to a potential delivery system for precisely the chemistry that subsurface oceans might lack, whether by design or accident, whether through intention or coincidence. 3I Atlas carries a key. In March, it will pass near the door. Whether the door opens, whether the key matters, whether anything waits behind the door ready to use what the key enables, these questions remain unanswered. But the signature is real, the nickel is enriched, the delivery will occur. And somewhere beneath Europa's ice, in darkness where sunlight never reaches and heat comes only from tidal friction, chemistry continues that might be waiting for exactly this element to complete reactions it has been attempting for billions of years. We measure the spectral lines, we calculate the abundances, we model the delivery mechanisms, and we wonder whether we are watching geology or witnessing the universe teaching us that life requires not just the common elements, but also the rare catalysts, delivered when needed by processes that operate across galactic scales and billions of years. The nickel glows in the spectrum, and in 4 months it will rain down on worlds that might finally have a use for it. Space missions are planned years in advance. Every observation sequence, every instrument activation, every trajectory adjustment undergoes review by committees that weigh scientific return against risk to hardware, power budget against data transmission capacity, mission objectives against operational constraints. Spacecraft are expensive, fragile, and irreplaceable once launched. Changing their plans requires justification that satisfies both scientific merit and engineering safety. Then the universe delivers an opportunity nobody planned for, and the committees must decide whether to chase it. Juno was designed to orbit Jupiter, to probe beneath the cloud tops, to measure magnetic fields and gravitational harmonics that reveal the planet's internal structure. The mission launched in 2011, arrived at Jupiter in 2016, and has been collecting data for nearly a decade. Every orbit is choreographed to maximize scientific return from instruments that measure radiation, plasma, magnetic fields, and atmospheric composition. The spacecraft has a primary mission, carefully designed objectives and finite resources. Observing an interstellar comet was not part of the mission plan. When the opportunity emerged, when trajectory analysts realized 3I Atlas would pass within 10 million kilometers of Jupiter during one of Juno's outbound orbit segments, Mission planners faced a choice: maintain the current observation sequence focused on Jupiter, or redirect some fraction of resources toward the comet. The decision was not simple. Juno's orbit brings it close to Jupiter every 53 days, and each close approach represents the only opportunity to collect certain measurements that require proximity to the planet. Missing one approach means waiting nearly 2 months for the next, potentially missing phenomena that operate on shorter timescales. But interstellar comets arrive far more rarely than orbital opportunities. Juno completes 7 orbits per year. Dickie Atlas might be the only interstellar visitor to pass near Jupiter during the spacecraft's remaining operational lifetime. The trade-off was not between valuable science and routine observation, but between 2 categories of valuable science with different risk profiles and different temporal constraints. The technical challenges complicated the decision. Juno's instruments were designed for Jupiter's environment, optimized for measuring intense radiation belts and powerful magnetic fields. Pointing them at a faint comet 10 million kilometers away meant operating outside design parameters, potentially reducing measurement quality, possibly risking hardware if pointing requirements exceeded safe limits for certain sensors. The plasma instruments might work adequately. Charged particles are charged particles regardless of source. But the camera system would struggle with the comet's faintness, and the magnetometer might have difficulty distinguishing the comet's magnetic signature from Jupiter's overwhelming field. Yet not attempting the observation meant missing the encounter entirely. No other spacecraft would be positioned to collect in situ measurements during the flyby. Ground-based telescopes could observe from Earth, but they could not measure magnetic fields directly, could not sample plasma populations in real time, could not provide the spatial resolution that even marginal spacecraft observations would achieve. The committees met. Engineers assessed instrument capabilities and pointing constraints. Scientists argued for scientific return and once-in-a-lifetime opportunities. Mission managers evaluated risk to primary objectives and long-term spacecraft health. The debate was not about whether the comet was interesting, everyone agreed it was, but about whether interesting justified the disruption, whether redirecting resources toward an unplanned target served the mission's broader goals, whether the spacecraft could safely do what was being asked. The decision came with caveats. Juno would observe the comet, but not at the expense of primary mission objectives. If conflict arose between Jupiter observations and comet observations, Jupiter would take priority. Instrument sequences would be adjusted to accommodate comet pointing only when that adjustment did not compromise scheduled measurements. Data storage and transmission would prioritize Jupiter data, with comet data filling whatever capacity remained available. These constraints meant the comet observations would be opportunistic rather than comprehensive. Juno would measure what it could when it could, collecting whatever data the instruments happened to capture while maintaining focus on the mission's primary target. The observation would not be ideal, would not match what a dedicated mission could achieve, but would provide unique perspective from within Jupiter's magnetosphere that no other platform could offer. Similar discussions unfolded for Europa Clipper. The spacecraft was still in transit to Jupiter, years away from beginning its primary mission studying Europa's ice shell and subsurface ocean, but its trajectory during late 2025 carried it through the predicted path of 3I Atlas's ion tail, offering a rare opportunity to directly sample material from an interstellar comet without deviating from the mission's cruise trajectory. The decision was easier here. Sampling the ion tail required no trajectory changes, no disruption to planned activities, minimal power expenditure, the instruments designed to study Europa's tenuous atmosphere could measure cometary ions with minor software updates. The spacecraft was already collecting cruise science data to test instruments and characterize the interplanetary environment. Adding comet observations to that program represented low-risk enhancement rather than disruptive redirection. But even low-risk decisions required justification. The science team had to demonstrate that comet data would not compromise instrument calibration, that the observation would not consume resources needed for later mission phases, that collecting this data served broader mission objectives beyond simple opportunism. The case was made, the observation was approved, and Europa Clipper spent 1 week in early November 2025 drifting through the comet's tail, collecting data that would take months to fully analyze. JUICE, Europe's Jupiter Icy Moons Explorer, faced different constraints. The spacecraft was using its high-gain antenna as a heat shield while transiting the inner solar system, limiting communication bandwidth to levels insufficient for transmitting large data volumes. It could observe the comet in November 2025, could activate cameras and spectrometers, could collect measurements. But those measurements would remain stored in onboard memory until February 2026, when thermal conditions allowed the spacecraft to safely deploy its antenna for high-speed transmission. This delay created uncertainty. Would the data quality justify the storage allocation? Would the observations reveal anything significant enough to warrant prioritizing their transmission over other science data competing for bandwidth? The decision to observe was made despite these uncertainties, based on the principle that opportunities to characterize interstellar objects were valuable enough to justify the resource investment, even if the specific scientific return remained unclear until the data arrived. These decisions repeated across every facility with potential observing capability. Hubble Space Telescope time is allocated months in advance through competitive proposal processes, where every hour is contested by research programs spanning all astronomical sub-disciplines. Creating space in the schedule for 3I Atlas observations meant displacing other approved programs, rescheduling observations planned long before the comet was discovered, requiring telescope operators to adjust pointing sequences that had been carefully optimized for efficiency. Webb faced similar pressures. The observatory operates under thermal constraints that limit where it can point, when certain observations can be scheduled, how long the telescope can observe particular targets. Fitting comet observations into these constraints required negotiation between the comet observing team and groups studying early galaxies, exoplanet atmospheres, stellar nurseries, and dozens of other programs competing for time on the most powerful infrared telescope ever built. Ground-based observatories are somewhat more flexible, able to adjust nightly schedules based on conditions and emerging opportunities. But even there, telescope time represents a scarce resource. Major facilities receive more observation requests than they can accommodate. Allocating time to 3I Atlas meant denying time to other projects, postponing observations of supernovae, variable stars, asteroid occultations, and countless other transient phenomena that do not wait for convenient scheduling. The allocations were made because the astronomical community recognized the comet's significance. Interstellar visitors arrive unpredictably, remain observable for limited periods, and provide information unavailable from any other source. When such opportunities emerge, the usual competitive processes for telescope time bend toward accommodation. Not abandoning normal priorities entirely, but acknowledging that some observations justify disruption because the alternative is missing the phenomenon entirely. Yet even with this accommodation, the observations remain constrained by what is physically possible with existing infrastructure. No telescope can observe the comet continuously for 4 months. Cloud cover, daylight, instrument maintenance, and scheduling conflicts create gaps in coverage. The March encounter will be observed intensively, with multiple facilities coordinating to provide redundancy and complementary measurements. But even that coordination will not achieve complete coverage. We work with what we have: a magnetometer designed for Jupiter that can barely detect the comet's magnetic signature, a camera system optimized for cloud features that struggles to resolve cometary jets, spectrographs calibrated for different wavelength ranges than the comet's emission lines fall in. We point these instruments at the comet anyway, extract whatever information they can provide, and acknowledge that better observations would require missions designed specifically for this purpose. But missions require years to plan, years to build, years to travel to their targets. By the time we could design and launch a spacecraft optimized for studying 3I Atlas, the comet will be beyond Neptune's orbit, fading into the outer solar system, becoming too faint for detailed observation. The window is now. The tools are what we have in place. The observations will be imperfect, limited by instrumental constraints and competing priorities, but they will be the only observations we ever make of this object. You stand in mission control, watching schedules update in real time as decisions propagate through the observation network. Juno's pointing sequence adjusts to include comet observations during the March outbound leg. Hubble's schedule shows the allocated time blocks, narrow windows when the telescope will turn from deep space surveys to track an object racing through our solar system. Webb's thermal constraints appear as coloured regions on planning charts, showing when the comet falls within observable zones. Each adjustment represents compromise. Each observation comes at the cost of something else not observed, some other science postponed or cancelled. The universe does not respect our schedules. It operates on its own timeline, delivers opportunities when and where it chooses, forces us to decide whether chasing the unexpected serves our understanding better than pursuing the planned. The committees made their choices. The resources have been redirected, at least partially, at least temporarily. The spacecraft will observe, the telescopes will point, the data will arrive. And whether those observations answer the questions we have about this comet or simply generate new questions we've not yet learned to ask, we will be watching when the moment comes. Because sometimes the universe hands you a deadline you cannot negotiate, a phenomenon you cannot reschedule, an opportunity measured in hours that will not repeat in your lifetime. And you adjust your plans, point your instruments, and hope that what you manage to capture during that brief window is enough to understand what you are witnessing. The telescope did not know it had made a discovery. It simply recorded pixels, comparing new images against archived sky surveys, flagging coordinates where brightness changed. The algorithm that analysed those images detected motion, calculated a preliminary trajectory, and assigned a priority score based on how unusual the object appeared. The score exceeded threshold. The system generated an alert and transmitted it to human astronomers who would decide what the detection meant. This is how astronomy operates now. Machines watch the sky continuously, processing more data each night than any human could examine in a lifetime. Algorithms trained on millions of known objects learn what normal looks like, then flag whatever deviates from that norm. The vast majority of flags are false positives, cosmic rays striking the detector, asteroids already catalogued, instrumental artifacts that mimic celestial motion. But occasionally, Perhaps once every few years, the algorithm catches something genuinely new. 3i Atlas was one of those catches. The Atlas Survey telescope in Chile images the entire visible sky every 2 nights, accumulating petabytes of data that record the positions and brightnesses of billions of stars and galaxies. When an object moves or changes brightness between observations, the software detects it, measures its properties, and compares those properties against databases of known objects. If no match exists, the system flags it for human review. On July 1st, 2025, the algorithm flagged a moving object in Sagittarius. The preliminary orbit looked wrong. Too fast, too steeply inclined, trajectory indicating the object was not bound to the sun's gravity. Within hours, other automated surveys confirmed the detection. Zwicky Transient Facility in California found it in archival images from late June. Additional Atlas stations in Hawaii and South Africa detected it independently. The orbital solution refined with each new measurement, and the conclusion became inescapable. This was an interstellar object, the third ever detected entering our solar system. Humans made the final determination, but machines did the discovery. Without automated surveys running every clear night, without algorithms processing terabytes of imaging data, without neural networks trained to recognize anomalous motion, the comet might have passed through the inner solar system undetected. It is not particularly bright, does not approach Earth closely, and appears in a region of sky crowded with stars where visual inspection would never notice one additional faint smudge moving against the background. Machine learning has transformed what we can find. Traditional astronomy relied on humans examining photographic plates or digital images, looking for objects that moved or changed between exposures. This worked when the sky was observed occasionally, when the data volume remained manageable, when interesting objects appeared bright enough to catch attention. But modern surveys generate data faster than humans can process. Pan-STARRS, Atlas, Zwicky, and future surveys like the Vera Rubin Observatory will image the entire sky nightly, detecting every object that moves or varies above threshold limits. Processing this flood requires automation. Neural networks trained on synthetic images of comets, asteroids, and transient events learn to recognize these phenomena with accuracy exceeding human performance. The networks operate continuously, never fatigue, never overlook faint objects, never let cognitive biases influence detection. They find thousands of asteroids, hundreds of supernovae, dozens of comets each year, and occasionally they find something that does not fit existing categories. The algorithms that detected 3i Atlas also characterized it. Photometry measurements tracking the comet's brightness over time revealed rotation periods, activity variations, and spectral signatures indicating composition. Astrometry measurements establishing precise positions enabled trajectory calculations that revealed the Jupiter encounter months before it occurs. All of this happened through automated pipelines where software extracted information from pixels without human intervention until the results required interpretation. But interpretation remains a human task. Algorithms can detect anomalies but cannot always explain them. When the spectroscopic data showed nickel enrichment, when the trajectory analysis revealed the Jupiter alignment, when the outgassing patterns displayed sustained directionality, humans had to evaluate what these patterns meant. Machines provided the measurements with precision no human could match. Humans provided the context, the physical intuition, The ability to recognize when multiple anomalies together suggested something more interesting than each anomaly individually. This partnership between human and machine intelligence represents modern astronomy's operational mode. Machines handle data volume, searching through billions of measurements to find the rare, interesting cases. Humans handle interpretation, connecting observations to physical models, recognizing patterns that might indicate new phenomena, asking questions that lead to deeper understanding. Yet the partnership raises questions about what we might miss. Algorithms are trained on known phenomena, learning to recognize patterns that appear in training data. When something genuinely new appears, something that does not match any category the algorithm was trained to detect, the system might overlook it or misclassify it as instrumental noise. We find what we teach machines to look for, and we teach them based on what we already know exists. 3i Atlas barely passed the detection threshold. Had it been slightly fainter, slightly slower, or moving through a different part of the sky, the algorithms might not have flagged it. Had the training data not included examples of hyperbolic trajectories, the orbit calculation might have failed. Had the spectroscopic analysis not included nickel in its template matching, the enrichment might have gone unnoticed. Each link in the detection chain involved algorithms making decisions about what merited attention, and any one of those decisions could have gone differently. This creates a selection effect. The interstellar visitors we detect are those bright enough, unusual enough, and similar enough to known objects that automated systems recognize them as worth investigating. Quieter visitors, objects that outgas minimally, that move more slowly, that appear less dramatically different from solar system comets, might pass through undetected. We are sampling a population, but we do not know how representative our sample is. The same concern applies to the anomalies we've identified in 3i Atlas. The nickel enrichment appeared in spectra because spectrographs were pointed at the comet and analysed for metal emission lines. The trajectory precision emerged from orbital calculations run because interstellar objects merit detailed analysis. The non-gravitational acceleration was detected because astronomers looked for deviations from purely gravitational motion. Each discovery resulted from humans or algorithms asking specific questions and performing targeted analyses. But what questions are we not asking? What patterns exist in the data that neither humans nor current algorithms recognize as significant? The comet's light curve might contain periodic variations that encode information about rotation states or surface features, but we might lack the analytical framework to recognize that information. The spectral features might include subtle signatures that indicate exotic chemistry, but our template matching might overlook compounds not in the reference databases. The trajectory might display fine structure that suggests control, but our orbital models might smooth over those details while fitting the data. Machine learning offers potential solutions to these limitations. Neural networks can be trained to find patterns in data without being told explicitly what patterns to look for. Unsupervised learning algorithms cluster data based on similarity, potentially revealing groupings that correspond to physical categories humans have not identified. Anomaly detection systems flag data points that differ from the norm, even when the specific nature of the difference is unclear. These techniques have been applied to 3i Atlas's data with mixed results. Unsupervised clustering of the spectroscopic observations confirmed the unusual composition, but did not reveal additional anomalies beyond those already identified through traditional analysis. Anomaly detection in the photometric light curve flagged several time periods where brightness varied unexpectedly, but follow-up investigation attributed these variations to instrumental effects rather than physical phenomena. The algorithms found what humans found, validating the discoveries but not extending them. Perhaps the more sophisticated question is what current algorithms cannot find because they were not designed to look for it. If 3i Atlas carries deliberate patterns, temporal modulations in outgassing, spatial structures in the coma, spectral features that encode information, we might need specifically designed analysis frameworks to recognize them. Searching for intelligence in astronomical data remains a nascent field, mostly focused on radio signals rather than chemical or dynamical signatures. But if directed panspermia operates through comets, if intelligent civilizations use such delivery mechanisms, they might embed markers that identify the comet as designed rather than natural. Not obvious artificial structures, those would be detected immediately, but subtle patterns that require careful analysis to distinguish from random variation. Perhaps periodic elements in the outgassing that correspond to mathematical constants. Perhaps isotopic ratios that deviate from natural nucleosynthesis in ways that suggest processing. Perhaps trajectory adjustments that maintain specific encounter geometries with precision, exceeding what random outgassing should achieve. Current algorithms might miss such patterns because they were not programmed to look for them, because the patterns fall below detection thresholds, or because we lack the theoretical framework to recognize them as meaningful. As machine learning advances, as we develop better models of what natural cometary behavior looks like, we might eventually build systems capable of recognizing when behavior deviates not just statistically, but systematically in ways that suggest intention. For now, the algorithms serve as extensions of human perception, processing data volumes that would otherwise remain unexamined, flagging phenomena that merit attention, enabling discoveries that manual observation would never make. They found through Atlas. They characterized its motion, its chemistry, its anomalies. They enabled the analysis that revealed this object as something worth studying intensively. Whether they will find the patterns that definitively answer whether this comet is natural or designed remains uncertain. That discovery might require algorithms we have not yet developed, training data we have not yet collected, analytical frameworks we have not yet conceived. Or it might require human intuition recognizing connections that no algorithm can make, seeing meaning in details that machines process as noise. The partnership continues. Machines watch, humans interpret. And together we try to understand what messages the universe sends, whether those messages are written in the physics of natural processes or in patterns crafted by intelligence we've not yet learned to recognize. Life might not be local. This simple statement carries implications that reshape how we understand biology, chemistry, and our place in the cosmos. If organisms can emerge in one location and spread to others, if the building blocks of metabolism can travel between worlds, between systems, between galaxies, then the origin of life becomes a distributed process rather than a singular event. Earth might not be where life began. It might only be where life arrived. The chemical evidence supports this possibility. Amino acids appear in meteorites, the remnants of asteroids that formed in the early solar system and occasionally fall to Earth. These amino acids are not contaminants from terrestrial life. Their isotopic signatures match extraterrestrial material, and their chirality includes both left and right-handed forms rather than the left-handed preference that terrestrial biology exhibits. They formed in space, through processes unrelated to life, demonstrating that the molecules biology uses can arise naturally in cosmic environments. More complex molecules also exist between stars. Radio astronomers have detected over 200 different molecules in interstellar clouds, including organic compounds like formaldehyde, acetaldehyde, and ethanol. These molecules form through chemistry driven by ultraviolet radiation and cosmic rays acting on dust grains coated with ice. Given sufficient time and the right conditions, simple molecules combine into progressively more complex structures, building toward the threshold where chemistry becomes biochemistry. Comets carry this chemistry. When they form in the cold outer regions of stellar systems, they incorporate whatever molecules exist in the protoplanetary disk. As they get ejected into interstellar space through gravitational interactions with giant planets, they carry that chemistry away from their birth system, preserving it in frozen stasis for millions or billions of years. When they eventually encounter another stellar system, they deliver their cargo, seeding young planets with organic complexity that might accelerate the emergence of life. This is natural panspermia, the process by which life's building blocks spread through galaxies without requiring intelligence or intention. It operates through statistics. If enough comets are ejected, if enough time passes, if stellar systems are close enough together, then eventually material from one system reaches another. The probability for any individual comet remains vanishingly small, but multiplied across billions of comets and billions of years, the cumulative probability approaches certainty. Recent exoplanet discoveries have revealed that organic molecules exist in many planetary systems. James Webb detected carbon dioxide and water vapor in the atmosphere of WASP-96b, a gas giant orbiting a star 1,150 light-years away. Spectroscopic observations of the TRAPPIST-1 system, 7 Earth-sized planets orbiting a red dwarf 40 light-years distant, suggest these worlds might possess the chemical ingredients for life. Observations of protoplanetary disks show that organic molecules appear even before planets fully form, incorporated into the material that will eventually coalesce into worlds. These detections indicate that organic chemistry is common, that the molecular foundations for life appear wherever conditions permit complex molecules to survive. But common does not mean identical. Each stellar system has unique elemental abundances determined by its formation history, by which supernova contributed material to the molecular cloud from which it condensed, by the specific nuclear reactions that occurred in previous generations of stars. Some systems will be carbon-rich, others nitrogen-rich, others metal-rich. The chemistry that emerges reflects these differences. This variation means that interstellar exchange matters. A comet from a metal-rich system delivers elements that might be scarce in a younger metal-poor system. A comet from a system where complex organic synthesis proceeded extensively delivers molecules that might take longer to develop locally. The exchange does not create life, but it enriches the chemical inventory available to whatever processes lead toward life, potentially accelerating timelines that might otherwise span billions of years. If we scale this process across the galaxy, if we consider that the Milky Way contains 200 billion stars and has been forming new stars for over 12 billion years, then the opportunity for chemical exchange becomes enormous. Older stellar systems eject material that eventually reaches younger ones. The galaxy becomes not a collection of isolated chemical experiments, but a connected network where material circulates, where successful molecular strategies can spread, where chemistry that enables life might propagate from systems where it first emerged to systems where it might otherwise develop more slowly or not at all. This is life as a galactic process, operating across scales that dwarf individual planets or even planetary systems. It suggests that when we search for life beyond Earth, we might be searching not for independent origins, but for branches of a distributed tree whose roots extend billions of years into the past, whose trunk spans light years, whose existence reflects not the special conditions of one world, but the common chemistry of an entire galaxy. 3I Atlas might be one seed in this distribution, one carrier in the network that operates whether any intelligence guides it or not. The comet's chemistry, the nickel enrichment, the carbon compounds, the organic molecules, could be naturally acquired, the result of formation in a particular stellar environment and processing during billions of years of interstellar travel. Or it could be deliberately optimized, the product of a civilization that understood panspermia not as philosophy but as engineering and chose to participate in the process. The distinction matters philosophically, but perhaps not practically. Whether natural or designed, the outcome is the same. Chemistry from one stellar system reaching another, expanding the range of molecules available to whatever processes unfold in the receiving system, potentially enabling reactions or metabolic pathways that local chemistry alone cannot support. When 3I Atlas passes Jupiter in March, when it delivers its cargo to moons that might already be chemical laboratories preparing for life's emergence, it will be participating in a process that might operate throughout the galaxy. Not unique, not special. Just one more seed in a distribution that has been operating since the first stellar systems formed, since the first complex molecule appeared, since chemistry first learned how to preserve and propagate itself across the void between stars. We are beginning to recognize this distribution. The discovery of interstellar objects, the detection of organic molecules in exoplanet atmospheres, the understanding that material regularly exchanges between planets within stellar systems. All of these observations point toward a universe where chemistry circulates, where molecular complexity builds over time, where the conditions for life do not arise in isolation, but emerge from processes operating across cosmic scales. If this view is correct, then Earth's biosphere might carry chemical signatures from elsewhere, molecular patterns that did not originate here but arrived on comets or meteorites billions of years ago. Our DNA might include sequences informed by chemistry from systems that died before our sun ignited. The amino acids in our proteins might follow templates established in interstellar space. Life on Earth might be simultaneously local and universal, uniquely adapted to this planet yet sharing molecular ancestry with processes unfolding across the galaxy. Testing these ideas requires technology we're only beginning to develop. Future missions to Europa, Enceladus, and other ocean worlds will search for life and characterize whatever biochemistry they find. If that biochemistry shows similarities to Earth life, if the molecular patterns match despite billions of years of independent evolution, it would suggest common origin or common delivery. If the biochemistry is completely alien, using different molecules and different strategies, it would suggest independent origin and demonstrate that life can follow multiple chemical pathways. Either discovery transforms our understanding. Either life is rare and its appearance on multiple worlds indicates distribution, or life is common and its diversity indicates that chemistry explores many solutions to the problem of self-sustaining complexity. Both possibilities expand the landscape where biology operates, moving it from the surface of one world to the surfaces and subsurface oceans of many worlds, perhaps to the clouds of Venus, perhaps to the hydrocarbon seas of Titan, perhaps to environments we have not yet imagined. This is the context in which we observe Three-Eye Atlas. Not just a comet, but potentially a participant in distribution mechanisms that operate across the galaxy, connecting stellar systems through chemistry, enabling the emergence of complexity by providing molecular building blocks that might otherwise remain unavailable. Whether that participation is accidental or intentional, whether the distribution operates through pure physics or includes guidance, remains the question we hope March's observations will begin to answer. But regardless of the answer, the comet reminds us that we live in a connected universe, that material moves between worlds, between systems, between galaxies, that chemistry circulates, carrying the potential for life with it, that when we search for biology beyond Earth, we might be searching for cousins rather than strangers, for systems that share molecular heritage, even if separated by light years and billions of years. The seeds drift between stars. Some fall on barren rock and go nowhere. Some fall on worlds with oceans and energy and time, where chemistry has been preparing for their arrival, where the molecules they carry might complete reactions that have been waiting for precisely this delivery. And we watch, measuring the seeds as they arrive, trying to understand whether we are witnessing accident or inheritance, coincidence or connection, randomness or the universe teaching us that life requires not just favourable conditions, but also chemistry that sometimes must travel across the void to reach places where it can finally grow. You stand beneath Europa's ice, in imagination, in the ocean that has waited 4 billion years in darkness. The water is cold but not frozen, heated from below by tidal friction, by the slow grinding of rock against rock as Jupiter's gravity flexes the moon's interior. No sunlight has ever reached here. No photosynthesis is possible. Whatever chemistry unfolds operates on energy, harvested from gradients between hot vents and cold water, between reduced minerals and oxidized compounds, between possibility and entropy. Above, 15 kilometers of ice shield this ocean from space, from radiation, from the chaos of the surface. But ice is not impermeable. Slowly, over millions of years, material from the surface works its way down. Cracks form and heal. Convection carries water upward and returns it laden with chemistry from the ice above. And occasionally, perhaps once every few million years, perhaps once every few 100 million, material from beyond Europa reaches the ocean. Dust from a comet. Molecules from interstellar space. Chemistry that formed under other stars, travelled for eons through the void, and finally arrived here. Maybe this is how life spreads, not through signals or spacecraft, not through deliberate messages or engineered probes, but through chemistry, through molecules frozen in ice, carried by comets that wander between stars, delivered to worlds where oceans wait in darkness for the catalyst that enables complexity to cross the threshold into self-replication, into metabolism, into life. Maybe we are not the gardeners. Maybe we are the garden. The comet continues outbound. By the time you read these words, it'll have completed its encounter with Jupiter, delivered whatever cargo it carried, and accelerated back toward interstellar space. The trajectory will carry it beyond Neptune by 2027, beyond the Kuiper Belt by 2030, into the space between stars where it will drift for millions or billions of years before encountering, perhaps, another stellar system, another opportunity, another chance to deliver chemistry to worlds that might be waiting. We will never know its full story. We will measure what we can during the brief window of observation, analyze the data for years afterward, publish papers proposing interpretations that future observations might support or contradict. But the comet itself will be gone, unreachable, carrying its secrets into the cosmic dark where our instruments cannot follow. What remains is the question it leaves behind. Not whether this particular comet was natural or designed, whether its chemistry was accident or optimization, whether its trajectory was coincidence or guidance, but whether we live in a universe where life's emergence is a solitary struggle on isolated worlds, or whether we live in a universe that distributes the tools for life, that delivers chemistry when needed, that operates seeding mechanisms we're only beginning to recognize, under Europa's ice, in Ganymede's buried ocean, on Callisto's ancient surface the delivery has arrived. Dust settles, molecules diffuse, chemistry begins exploring new combinations, new pathways, new possibilities enabled by elements that were not available before, by compounds that took billions of years to synthesize, by catalysts delivered from beyond. Perhaps nothing will come of it. Perhaps the oceans are empty, or the chemistry is wrong, or the energy is insufficient, or the time is not yet right. Perhaps the delivery makes no difference at all, or perhaps, somewhere in the darkness beneath the ice, a reaction that has been attempting to proceed for billions of years suddenly finds the cofactor it needed. Perhaps a metabolic pathway that could not complete for lack of a single element suddenly gains access to that element. Perhaps chemistry crosses a threshold it could not cross alone, and life, patient life that measures its progress in geological ages, takes another step toward complexity. Not because it was created, not because it was designed, but because it was given, by chance or intention, by physics or by purpose, the chemistry it needed to continue the process it began billions of years ago in darkness, in water, in environments where metabolism requires not sunlight but only molecules that want to react, and the catalysts that allow them to do so. The comet glides away into the dark. Its trajectory bends around the sun's gravity, aims toward the constellation Gemini, toward the spaces between stars where silence and cold preserve everything indefinitely. In 1,000,000 years, it will be a light week from the solar system. In 1,000,000,000 years, it might encounter another star, another planetary system, another chance to deliver its cargo, or it might drift forever. One seed that never found soil, one delivery that never reached its destination, one more fragment of ice and chemistry, joining the countless others that wander through galactic space, carrying the potential for life, but never meeting the conditions where that potential can be realized. But here, in the system it just departed, beneath the ice of moons that have waited since the solar system's formation, chemistry continues. Reactions proceed, complexity builds, and whether that complexity ever crosses the threshold into life, whether it ever develops metabolism or replication, or the organized persistence we recognize as biology, the delivery has been made, the seeds have been planted, the garden waits, and we, standing on our own world under our own star, watch and wonder whether we too are the result of such planting, whether Earth's biosphere carries molecular patterns delivered from elsewhere, whether life here began not in isolation but as part of a distribution that operates across the galaxy, connecting stellar systems through chemistry rather than signals, through matter rather than information. Maybe that is the true meaning of the comet's visit, not the answer to whether this specific object was natural or designed, but the reminder that we exist in a universe where matter moves, where chemistry circulates, where the building blocks of life might travel between worlds as naturally as light travels between stars, A universe where life does not arise alone but emerges from processes that span light years and eons, where every world with water and energy and time might be waiting for the right chemistry to arrive, where comets are not just debris from dead systems, but potential couriers carrying complexity from places where it already emerged to places where it might emerge next. The comet departs, the garden waits, and beneath the ice in the darkness, chemistry begins to explore what becomes possible when new ingredients arrive from beyond the light.